Are you all right?
Yes. Would you excuse me for 1 minute, dear?
Oh, of course, Doctor.
Igor? May I speak to you for a moment?
Of course.
Sit down, won't you?
Thank you.
No, up here.
Oh, thank you.
Now, that brain that you gave me, was it Hans Delbrück's?
No.
Ah, good. Would you mind telling me whose brain I did put in?
And you won't be angry?
I will not be angry.
Abby someone.
Abby someone. Abby who?
Abby normal.
Abby Normal.
I'm almost sure that was the name.
Are you saying that I put an abnormal brain into a 7.5-foot long, 54-inch wide gorilla? Is that what you're telling me? Quick, get up!
What? 3 syllables, yes?
I wonder who that could be at this hour.
Well, good morning. As you might have guessed from the movie clip today, this is all about research today. And what I think you'll see, though, is our concept of research is slightly different than what was actually depicted. So my name is Dr. Tim Yateman. I'm relatively new to Spartanburg and the Gibbs Cancer Center. I'm the Gibbs Cancer Center director. And I'd like to welcome you to the first ever Space, Cancer, and Personalized Medicine meeting. The meeting today is hosted by the Gibbs Cancer Center and Research Institute, by the Center for Advancement of Science and Space, and by VCOM, our partners here in the auditorium. During the course of the day, you'll have the opportunity to listen to a very distinguished group of local and national speakers who have traveled quite a distance to the upstate. Some took 6 hours last night to get here, to kick off what we think will be an annual one-of-a-kind meeting to capture some of the latest advances in science and research. The meeting would not have been possible without substantial efforts to the conference organizers, such as Kristen Lacey and her staff from the Gibbs Cancer Center, Patrick O'Neill, Dwayne Ratliff from CASIS, and Mark and Alexis from VCOM. Before we get started, I'd like to make a few housekeeping reminders. So please silence your cell phones. That's the first thing to the conference, and hold questions until the end of the presentations. I'd now like to introduce the CEO and President of the Spartanburg Regional Health System, Mr. Bruce Holstien, who will take it from here. You should hit the button.
Good morning. Welcome to our friends at VCOM, NASA, CASIS, Spartanburg Regional, St. Francis Health, Providence Health, Mercy Health, and our community supporters. I believe there are at least 2 people here that actually came back from the Masters to be here. So we thank both of you for making the trip back. I also thank Dr. Yateman for the development of this conference and his ongoing life work to find cures and improve treatments for cancer. We're extremely honored to have him lead our team. Back in 1971, the Nixon administration declared war on cancer. Since then, we've learned much. We actually know environmental causes of cancer, and we know personal behavior causes of cancer, things like smoking. We know early detection is critical, and treatments have steadily improved, now rapidly evolving into the molecular realm. Through our early research work at the Gibbs, philanthropy, recruitment, and top scientists, and partnerships, we recently completed a new phase in our evolution to continue the attack. Our new research lab opened yesterday and was dedicated and continues our necessary and critical work in molecular medicine. As part of that effort, I am pleased to introduce Dr. Jack Pledger. Dr. Pledger joins the Gibbs after 20 years at the Moffitt Cancer Center and extraordinary work at Harvard, UNC, and Vanderbilt. At Vanderbilt, Dr. Pledger built really a one-of-a-kind and incredible research center with more than $80 million in annual NCI funding and led them to record-time NCI status. Please join me in welcoming Dr. Jack Pledger as our moderator today.
Well, thank you very much, and I am delighted to be here and to see each of you in attendance. I'm very excited about this conference because, as you know, I think research is the hope in cancer. And without research, I think it limits the hope for the progress that will be made. I anticipate right here in the upstate region that we're going to be able to make progress and be able to explain that progress in many meetings just like this. Once again, I would just like to thank the leadership at the Gibbs Cancer Center, because they presently have a great cancer center, but they got together and they said, you know, we can make it better. And I believe that we're going to see that happen. Now, my job is just to moderate the panel and to moderate the discussions and to keep people on time, including myself. So our first speaker is going to be Dr. Craig Kundrot. Now, Craig is the chief scientist for NASA's Human Research Program. Now, the Human Research Program conducts research to understand the level of human risk and performance in space. Now, each of you know something about this, and I know something about this because I've seen the movie Aliens, and there's a lot of risk up there. And I think that's maybe what we're going to hear about. But Craig comes to us. He's a graduate of Northwestern and Yale University. He's an X-ray crystallographer, and his own research has been conducted at the highest level and now is directing the program for human risk. We're just delighted to have him come to be a speaker, and he'll be talking to us about the space environment's effect on human physiology. Craig?
Thank you. Are you unmuted? No, I'm on, I think. Okay, thank you very much. It's a pleasure to be here this morning, and I'm particularly comfortable here this morning. Not only the South Carolina hospitality, but it's unusual for a conference like this to have bookends of a crystallographer starting and also to have crystallization at the end of the day. And so Gibbs Cancer Research has given us great hospitality. And here at VCOM today, coming from NASA, where we largely speak only in acronyms, it's a delight to be at an institution that refers to itself by an acronym, VCOM. So thank you very much. And this is a very nice facility. We are not going to talk about the aliens today. I'll take the questions at the end on aliens, but that won't be the subject right now. What we're going to talk about is the space environment and its effects on human physiology. And this whirlwind tour has really three components. When we talk about the space environment, what do we really mean? What are the underlying factors that really impact physiology? Second, what are the time courses of the changes, just at a high level? And then we'll delve a little bit deeper into some of the areas of larger change. All right, so the first aspect of the spaceflight environment is the acceleration environment. And we usually think about the weightlessness component. For some things, like neurovestibular responses, it's important to note that there's also a change in the acceleration environment at launch and during landing. For the moment, though, we'll focus on orbit and look at what does this weightlessness really do on orbit? What's its physical manifestation? All four of these aspects can be sensed at the microscopic level or the macroscopic, or both. So the first is reduced sedimentation. Without a density difference, objects do not settle. Astronaut Mike Fink here is verifying that fruit does not sediment on the International Space Station. In addition to sedimentation, you no longer have buoyancy-driven convection. So hot air, for example, will not rise. So an exercising human is going to have a different challenge dissipating heat. You won't have that natural convection at work. Thirdly, hydrostatic pressure. As I'm standing here, there's this hydrostatic pressure gradient in my body. That disappears. You'll see in a moment that that figures prominently in the cardiovascular system. Body forces. Running on a treadmill in weightlessness is very easy. It also does you no good. And so as you'll see, there's a picture that you have to wear a harness that secures you to the treadmill with bungee cords to basically give you about a 75% body weight force against the treadmill and get the benefits of treadmill running. So these four things are really the four components of weightlessness that really affect physical and biological systems. So when you say spaceflight environment and weightlessness, it's really one of these four things or a combination of them that are really at work. Another aspect of the environment goes by the acronym ICE, for Isolated, Confined, Extreme Environment. And this affects psychology and physiology. Now, we're not going to have time today to talk about the immune system response, but one thing that we find is that the folks that do a winter over in Antarctica have a very similar change in immune function that our astronauts do with 6-month missions due to the isolated, confined, extreme environment. So some of the features here of that environment is the monotony. So this is hard for us to imagine because we don't experience this every day. But here's a picture of Valery Polyakov in the space station Mir looking out at the space shuttle Discovery as it's about to dock. He spent 14 months, over 14 months on Mir, that's the world record for a long duration stay. Imagine spending 14 months in a small home. And the number of people that you interact with face to face during that time, you can count on one, maybe two hands. You interact indirectly over radio and video, back to Earth with more, but your actual repertoire of people that you deal with is far reduced. Your physical environment is the same day after day after day, and this is very taxing. And the folks that do the winter overs in Antarctica experience the same types of trouble, or challenge, I should say. In addition, if we're talking about exploration missions going beyond low Earth orbit to asteroids, the moon, Mars, in the case of Mars, you'll be so far away that at the speed of light, communication takes 20 minutes just to travel one way. So a conversation has a 40-minute, interruption or lag. You're obviously not going to have a very good real-time conversation with folks. So you have the sense of physical remoteness and danger, and also the challenges of communication with the folks back home. In an ice environment, you're lacking the diurnal cues that help entrain your circadian rhythm. On the space station, you're going around every 90 minutes. That's a pretty short day. So your external lighting cues, not that you have a lot, there's not a lot of windows, but the extent that you have them, those are not going to help you. If you're on a mission to Mars or another deep space mission, you're still going to be lacking the usual cues. And what we see down here on the bottom right are just some graphs from a paper from a simulations the Russians did. They had 6 crew in a facility that was enclosed for 520 days, and they were mimicking a Mars mission. And these graphs indicate their activity levels and some of their some cognitive measures and how over time they drifted. And circadian entrainment was a big issue for these folks in this enclosed environment. In terms of workload, this is another big challenge. We have this comm delay, so we're going to have crew that are a lot more autonomous than they are in low Earth orbit. And balancing the right level of autonomy with the right level of workload, so too little work and too much work are equally bad, is a challenge. And when they're remote, you got to get that balance right, or you have a headache because you cannot return quickly. And then lastly, in these ice environments, you have all the interpersonal dynamics at work. You have the interactions with the ground crew and family and friends back home. That's going to be quite a challenge with these communication delays, et cetera. It's going to be lean communication compared to what you're used to in normal life. And then you have your interactions with your crew members, which you have month in, year out on say a 30-month mission to Mars, all under a very unusual and strained condition. So all these contribute to psychological pressures that can translate into physiological manifestations. The last big aspect of the spaceflight environment is radiation. And this is novel in our experience because most of what we're exposed to terrestrially, naturally and through medicine, are photons. But in space, the important radiation component actually comes from the periodic table. It's basically from hydrogen on up to iron and beyond. Those elements are present, stripped of their electrons, and they're moving at fractions of the speed of light. Okay? That's for the galactic cosmic rays. I'm getting a little bit ahead of myself. Let's talk about the solar particle events first. So we have, for space radiation, two components. One is from the sun, solar particle events. One is from deep space, galactic cosmic rays. The solar particle events are, the good news is, well, the bad news first. The bad news is we can't really tell when they're going to happen, right? It turns out that just yesterday there was a class M6 solar flare. So that's the biggest of the year. And we have until tomorrow until it hits, okay? So there's, the bad news is we cannot predict when they're going to happen. The good news is we A, have warning, and B, they're made up largely of protons and helium, and they're relatively low energy, so we can shield against them. So operationally, we can make sure that crew are not out on a spacewalk. They have time to get back into the habitat and like a storm shelter and wait out the storm if need be. So those are not a huge problem. The bigger challenge comes from galactic cosmic rays, which are thought to result from supernovas in the galaxy. They're present at essentially a constant rate. But as they impinge our heliosphere, this is the area that's influenced by the sun, our solar cycle modulates how much actually gets to our vicinity by about a factor of 2. So during solar max, the GCR rate is down about 50% of what it is when the sun is at its solar minimum. It is made up, as I was saying a moment ago, it has about a 1% component that is heavy nuclei. Say iron, for example, has a charge of 28 on it. So these particles are moving at fractions of the speed of light. They're very high energy, and they deposit, as we'll see a little bit later, very dense energy track, deposit energy over a very long and continuous swath. Very different than photon exposure. Unfortunately, shielding is very difficult. We have yet to find a practical way to shield against these very high energy particles. And in fact, if you do it wrong, you actually make the problem worse, because as the particles come in and interact with matter, they can fragment and generate secondaries, and you actually have more particles on your hand than you began with. Fortunately, the exposure levels are on the low side, about 1 milligray a day. So these are the three major components of, when we say the space environment, the three major things that are important for human physiology. The weightlessness, and remember those four, we can break that down into four more fundamental properties. The isolated, confined, extreme environment, and the space radiation. All right, so let's look at, in broad terms, what happens to the physiology. So this is a chart which experts in these disciplines hate, okay? But it's a very good conceptual orientation. So I want to stress that it's a notional chart, but what we're showing here is the magnitude of decrement in arbitrary units plotted against time. Here, launch, time after launch in weeks. So the very first response happens basically immediately upon encountering weightlessness, and that's a challenge to the sensory motor system. In the first 2 or 3 days, the crew are at risk of developing space motion sickness. Okay? After that, we'll talk more about this in a moment, After that, there's an adjustment. That's really not so much a threat any longer, but there are still some residual adjustments that need to be made. The next fastest change physiologically is within the first week, there's a reduction in plasma volume. And we'll talk about that in a moment. Following that, about a week later, is a reduction in red blood cell mass. Now, the next three curves or lines are particularly notional for several reasons. First, we have, in the absence of countermeasures, a decrement in muscle function. Okay? And it's shown here as a straight line. We don't really, that's really very notional. It's not necessarily a straight line. And exactly what slope you peg it at depends on what countermeasures you're using in flight. Okay? And we'll talk about that a little bit more. Same story for bone. It's not necessarily linear. We have very little, essentially no good data on orbit for what the decay looks like. Most of our data are for 6-month intervals of flight. And depending on your countermeasure regime, the slope of this line changes dramatically. And then lastly, we have radiation, which, as we'll discuss later, is still, we're still trying to get a handle on the exact nature of the biological damage and the response. It's quite possible there are threshold effects here. So what's depicted here is really that you're just getting a milligray a day, and your chances of some ill effects are rising attendant with that. So this gives you a feel of the time scale of changes, that a lot of it's occurring within the first minutes and days, a couple changes over weeks, and then others persist for the weeks into the mission. Upon return, we have a similar graph, but now we've changed the x-axis to time after landing in terms of months. Sensory motor, again, we have another G transition, going from now the weightless environment to back to the G field. So there's another transition where motion sickness is an issue, and getting the neurovestibular system trained back up for that 1G environment takes on the order of a month to fully recover. And so astronauts who return, for example, cannot drive their cars right away. They have to wait a couple weeks before they can do that. Another thing that is immediate is orthostatic hypotension. We'll talk about that shortly. So that recovers in a matter of days. Red blood cell mass and muscle recover on the time scale of a month or two. Bone, however, takes a year and a half, plus or minus 6 months. It takes a while to build bone mineral density back up. So usually when we're talking about the spaceflight effects on human physiology, we're thinking about the in-mission changes. But it's also important to note that rehabilitation back on Earth is also a significant challenge. All right, so let's look at some of these in more detail. The first is the sensory motor, the one that changes most quickly. And these challenges arise basically because of conflicting inputs from the vestibular organs, the otoliths in particular, compared to vision and the proprioceptors. The otoliths are constantly sensing the G field. And when you go to weightlessness, that signal is turned off. And so one of the leading ideas is it's that sensory conflict that sets up the challenge to the neurovestibular system. So 70% of crew experience some form of space motion sickness. It might just be a mild, nausea, or it might be something that actually, prompts vomiting. Happily, this is only an issue during the first 2 or 3 days of the transition. Promethazine is often used to quell this, and just very careful, intentional use of head movements is another way to help keep this under control, both in the transition to flight and the return back to Earth. After those first 2 or 3 days, there are still some lasting perceptual challenges. On the ocular motor control front, there's changes in both static and dynamic visual acuity. Smooth pursuit eye movements are a bit of a challenge. Vestibulo-ocular reflex and degraded eye-head coordination and target acquisition. So when you see a word like target acquisition, you can think like docking spacecraft. This can be a challenge. Hand-eye coordination, spatial orientation, these are all a bit challenging for the astronaut. And that can lead to the need to focus on those kinds of tasks more intentionally. And so on the cognitive front, the crew sometimes has to basically be dual tasking, paying a lot more deliberate attention to the sensory motor system while they're conducting their other tasks, say a docking or whatever. So sensory conflict seems to be the core issue here, and there are some countermeasures available. We're not real happy about the use of promethazine and some of its side effects, and so we're still looking for improved countermeasures here. On the cardiovascular front, now this changes more on the hours to weeks time scale. The first thing that happens is a change in plasma volume, which leads to ultimately orthostatic intolerance, not on orbit or in flight, but upon return back to Earth. And the sequence is as follows. When going into 0G, there's a cephalid fluid shift. So the hydrostatic column that's present right now disappears. So fluid migrates up towards the head, and receptors identify this as Craig has perhaps consumed too much liquid, and we'll send him to the restroom, and over the next couple days, I will lose 1 to 2 liters of net fluid, and my plasma volume will go down. In addition, because my baroreceptor system is not being challenged daily with, going from sitting or lying to standing posture, it sort of becomes desensitized. So in flight, this is not an issue. But upon return to Earth, there's insufficient plasma volume and a slowed down baroreceptor reflex, and I am susceptible to fainting upon return to Earth. Lagging the plasma volume change is a change in aerobic capacity due to a decrease in red blood cell mass. So the fluid excretion increases the hematocrit, so there's decreased EPO production, then there's decreased RBC, red blood cell production, and restored hematocrit. So you get the hematocrit restored, but net, you're down in total amount of red blood cell and hemoglobin due to your oxygen transport. There's also a reduction in the left ventricular mass, and all this leads to a reduction in aerobic capacity, which we are still, well, I'm coming to that, working on a good countermeasure for. There's another risk that is really more of an a priori risk. We don't have really good demonstrable data that says this is a problem in space, but it's something we have our eye on, and that is the risk of arrhythmias due to changes in electrical conduction as the ventricular mass is changing and the environment right around the heart is changing. So we have investigations looking at that. In terms of countermeasures, the orthostatic intolerance is pretty well under control, although, like I said, we would like things that are a little bit more free of side effects than, say, promethazine. So amongst the things that can be done, 2 things that can be done in flight are there's a couple of devices to supply a lower body negative pressure, which pulls fluid back into the lower limbs. So that's done in flight to sort of get the system retrained for the hydrostatic pressure challenge that's going to happen upon return to Earth. Similarly, there's an occlusion thigh cuff that can be used to force fluid pooling in the lower limbs. Then right before flight, fluid loading. Increased consumption of basically water and salt tablets, i.e. saline, helps bump up the total volume of the system for the return. And then compression garments can be worn, compression hose, basically, stockings, to help prevent fluid flow into the limbs when the hydrostatic gradient is reestablished on Earth. And liquid cooling garments just help with the thermal regulation. So that's manageable, though we'd like better countermeasures. The aerobic capacity is still eluding us. We use treadmill and cycloergometer exercise to try and bring the VO2 max levels up, but they still seem to be about 15% reduced from what the terrestrial values are. So again, on orbit, this is not a great challenge because there's not a great need for aerobic activity, but when one is thinking about landing on Mars and what kind of activity the crew can undertake at what point, after landing, this is something that we would like to improve upon. The next set of responses are the musculoskeletal. The unloading that's occurring now in weightlessness, the lack of body forces, leads to bone loss. So that's, demineralization. That's going to reduce the strength of the bones and increase the risk of fracture and perhaps lifetime risk of osteoporosis. Secondary to that, there's an increased risk of renal stone formation. And that would be a bad day to be on a, 7 months into your, voyage to Mars. You've landed, you've been there a month, and you have a renal stone. That would not be a good day. Along with the bone loss, there's muscle loss, both in terms of strength reduction, power reduction, and endurance. And then there's also, it's not so much a problem, but really something that needs to be designed for, is spinal elongation. So again, with this lack of body force, the spinal column, the seated height is the NASA term for it, increases up to 6% in flight. And so designers of spacecraft, when they're working out what controls can be reached and also what seat liners are used for reentry, for a conformal seat, have to take all this into account. On the bone loss front, we actually are doing very well. After decades of work on this, it looks right now that the combination of the treadmill, I left that off the chart, but the treadmill, the resistive exercise, and bisphosphonates, looks like it might actually completely arrest the loss of bone in flight. Now, there's a little caveat to that, and if you were watching the video before our meeting started, you saw a demonstration of some of the exercise equipment. And the exercise regime we're using on the International Space Station right now involves 3 pieces of hardware, each of which involves about a home refrigerator size device. And that's a lot of mass, that's a lot of volume, and it's not clear we can take that out for exploration missions. But at least we have an existence proof that given the right loads on the body and the bisphosphonates, we might be able to arrest bone loss. Muscle atrophy is a larger challenge. The current aerobic resistive training is improving things, but we're still seeing about a 5% loss in muscle strength. Better than before, but still not arrested. And we also see a highly variable response in people. So we're also trying to reduce that spread. Now, the next area of physiological response is really quite broad and one we're still trying to get a handle on. And this is the response to radiation. As we mentioned before, terrestrial radiation exposure is primarily photons. But in space, we're seeing protons and heavy nuclei. Those are particularly of concern. And the secondaries that are generated through shielding. So I don't know if you can see this very well, but I want to focus your attention to 2 panels here. This is a picture of biomarkers for fluorescent markers for double-strand breaks for an exposure to X-rays where you see a pretty uniform pattern, and then this is particularly dramatic. For the same dosage, here's a pattern from iron, and you can see 3 tracks here indicating that there's a very dense ionization trail that is breaking DNA along the whole length. And over here on the right side, you see just particle tracks for various nuclei and just how dense these heavier elements are. And so we have a different type of biological damage because there is so much energy deposited in such a small space. You don't just introduce a single strand break here and one over here, or a double strand break here and one there. You may wipe out an entire nucleosome and 200 base pairs of DNA. That's a different kind of biological damage. You are leaving an ionization trail, across a tight junction, between cells. There's still a lot that we are learning about the nature of the biological damage and the response. In terms of categories, we're concerned about acute radiation syndromes during the mission. If for some reason we don't have adequate protection against those solar flares, what's our acute radiation risk? Another risk is to the central nervous system. We're looking at, in animal models, like damage to the hippocampus, for example. What will happen in a mission, a 30-month mission to Mars? What will happen post-flight in terms of long-term health and, say, early onset Alzheimer's or other diseases? Cancer is not an issue really in mission, but really post-flight. What does this radiation exposure, which might be on the order of a sievert, do to lifetime risk for cancer? And then several degenerative processes as well are concerned for post-flight. So right now, our efforts are really focused on understanding both phenomenologically and mechanistically, the nature of the damage and the biological response. And until we have a better handle on the mechanisms, we're not really putting a lot into countermeasure development. So this is a big challenge for us because it is so different than anything terrestrially. Okay, the last response was not on the earlier charts, and that was deliberate. And that's because it's a recent finding, and it's an example of why the International Space Station is such a valuable platform for studying the human system. And this is the visual impairment intracranial pressure problem, which in our acronym world at NASA we call VIIP, V-I-I-P. What I'm showing here are statistics from the first paper that came out to characterize this syndrome. In the initial observations, there were 7 cases. It turns out as we refined our definitions, we would now say 19 out of 25 subjects show these symptoms. There's a number for which we don't have adequate pre-flight data to say whether or not they developed some of these problems post-flight. So the incidence rate is about 76%. So so far it's only been seen in males, and the types of problems that we see are elevated intracranial pressure, hyperoptic shifts, choroidal folds, and optic disc edema, increased optic nerve sheath diameter, cotton wool spots, globe flattening. Now, some of these symptoms resolve post-flight. In some subjects, some do not. So this is a very active area of investigation. One of the leading hypotheses is it's due to this cephalid fluid shift of blood. It could also be CSF fluid shift. There could be contributing factors from a very high sodium content in the diet, from relatively high CO2 levels on the ISS. There's a number of hypotheses there, and so we are very actively trying to deploy non-invasive measures on station and direct measures so we can actually get in-flight data and a more detailed characterization of what's happening to intraocular pressure, ICP, the cardiovascular system, et cetera. That's an excellent example of why the long-duration flights on station really help reveal to us risks that are present for the long-duration space flights for long missions to asteroids or to Mars, for example. So that's our whirlwind tour of the stimuli and responses to physiology. If you would like to know more from the Human Research Program perspective, I refer you to this website, humanresearchroadmap.nasa.gov. The Human Research Program, or HRP in our vernacular, is focused on understanding and reducing the risk to crew health and performance in exploration missions. So there are 32 risks, explicit risks that we're looking at. Half of them are physiological. And in all cases, we have an evidence base that defines the risk. Given the risk, we define gaps in our understanding about the risk or our ability to mitigate, or both. Having identified these gaps, we then identify tasks, that's our term for research investigations, which produce deliverables that will fill those gaps, change the risk posture, and our evidence base. So there's a lot of detail here. If you go to this website and click on the evidence tab, there's an evidence report that describes the state of knowledge for each one of these 32 risks. So to summarize then, in terms of the spaceflight environment, when we say spaceflight, in broad terms, we really mean 3 things. We mean the acceleration environment, and in particular, there are those 4 things, the sedimentation, convection, hydrostatic forces, and body forces at work. There's the isolated, confined, extreme environment, and there's the radiation. Those are the real properties of, quote, the spaceflight environment. The responses to these stimuli can range from seconds for neurovestibular to years for bone and cancer, for example. There are several types of responses that we went over, and if you would like more detail, again, I refer you to the humanresearch.roadmap.nasa.gov website. So thanks very much for your attention and for the opportunity to share this with you today. Thank you.
Okay, so I can allow maybe 2.5 minutes, 3 minutes for questions. So do we have any questions? I'm sorry, yes, David. Okay, the question was any problems with blood clots,
Yes,
DVTs?
Yeah, right. The question is there a risk for DVTs? Operationally, no, because they are exercising on average. Well, the time allotted for exercise, which is another aspect of our countermeasure challenge, is 2 to 2.5 hours a day. Now, that's not really all exercise time. There's assembling and deassembling equipment and other things, but the point is they are actively exercising every day. However, if they weren't, this would be a risk, because if you saw the video earlier, you find that on Earth we're locomoting with our legs all the time. On station, they're swimming, and so that would be a risk. But their exercise regime basically makes that a non-issue.
Yes, in the back.
So, quick question. I was wondering if there have been any studies on lymph flow through the lymphatics and perhaps leukocyte ability for them to get into the lymph nodes.
Yeah. So the question is, fluid flow through the lymphatic system, and that has not been studied in flight. That is a concern, or maybe not concern, but that's a known contributing factor that that's going to change the dynamics in the immune system. The immune system has been studied, and it's a complicated, it's not real simple response. There is dysregulation. We don't know yet if that really poses a long-term threat, but we see things like increased viral shedding and the rest. And some of this, it may be due to the microgravity environment, but some of it is also stress-related. So, for example, some of the viral shedding actually starts very shortly before launch. So it's a stress-induced factor. So teasing out what is stress, what is physiological, like with the altered fluid flow, is yet to be teased out.
Okay, thank you. And maybe you can reserve your question for the breaks in just a few minutes. I'm trying to keep us on schedule. I have my questions here, and as soon as the breaks hit, I'll ask you about signal transduction and what were on some of your charts. What were those percentage of those fold increases, or just a few percent, okay? But Craig, thank you very much. Before I introduce the next speaker, I would just like to, once again, just in terms of my own feeling about being here at the Gibbs Cancer Center, I'd like to express my appreciation to several folks that are here. One is Dr. Bearden, along with Dr. Josie, who have been longtime really supporters and developers of the Cancer Center model here, and then, of course, to Mr. Gibbs, who's in attendance here today. And with the questions and discussions and his getting into cancer, I think by the end of the year we'll probably have to award him a Ph.D. in cancer research. So I do want to acknowledge those folks. So let me now introduce to you Dr. Neal Pellis. So this is somebody that I got a chance to interact with yesterday, and it was really delightful. He's the director of the Division of Space Laboratory Sciences at the University Space Research Association in Houston. As it turns out, he really likes a lot of the best restaurants in Houston. I speak highly for one that he likes, Mogul's. So we share those in common. But I will point out that he's received a Ph.D. in microbiology and then went on to do a postdoctoral fellowship at Stanford University. He's held faculty positions at Northwestern University Medical School, at the University of Texas Medical School, then at MD Anderson. And he's been very busy there and has had numerous roles with the space program. And he's here to tell us about cell biology and tissue engineering in microgravity. And tissue engineering, is that like the evolutionary process that we have for making new tissue, or is that? Well, we'll hear more about it. Neal?
Okay, I think I'm connected. While he's doing that, I'll just thank the Gibbs Cancer Center, CASIS, and VCOM, and the other sponsors, and Tim for inviting me to do this. It's a great pleasure to have to do this and give the kind of presentation in this environment. It's also interesting that I'm following Craig Kundrot, because that's something I used to do many years ago when I was at NASA, and it seemed like we were always paired up in this order. So He's a tough act to follow sometimes, but we're going to work on it. He did me some favors. I might have to actually skip some slides. That's interesting. Why are we getting a... I'm done. Where's the next restaurant?
See where you have trouble advancing.
Let's try it that way. Okay. All right. We're okay. So it's going to be on cell biology and tissue engineering. But I'm going to talk mostly about the tissue engineering side for this. And I'm going to ask the simple question, why do we want to even talk about engineering tissue in space? And we engineer tissues because of their value in research. There's a potential for replacement tissues that can be envisioned in some of the strategies that are being put forth, even without the space program. A much greater proportion of it is done outside. Some of it a little north of here in your sister state at Wake Forest has one of the largest tissue engineering groups in the United States. And so it's something that could be very familiar to some of you. We get some reasonable models of human disease out of them. There's opportunities to do drug testing like we wouldn't have otherwise in standard culture, and we might be able to get into a little bit of that. And the other thing about it is that when you put cells into unusual environments, their adaptive phase sometimes will reveal a number of novel things to you that you hadn't seen before. And secondly, as a product of that, a lot of times we can get opportunities to look at various molecules as biopharmaceuticals, and maybe this be a production venue for that. So that's it. Why microgravity? I think Craig already gave you a lot of this information. The first one is obvious from his talk, and I'm not going to go into that. The second, they have a greater tendency to self-associate because they're not sedimenting. And it's an unusual observation. And we wondered, just what mediates this. Are we looking at ligand-receptor interactions? Are we looking at adhesion molecules that are involved in this? What is it? And much to our surprise, it's probably those only after they come together. What brings them together we don't quite understand, because we now know that any particle you suspend in space will have a tendency to agglomerate with time, all on its own. We've taken in, the fluid phase doesn't have to be liquid, it could be a gaseous phase, and it'll still do the same thing. You take non-dairy creamer and shake it up in a plastic bag and get it suspended, and you watch it for a couple of days, you notice that they're starting to agglomerate. So it's kind of an interesting property that takes place, because that's probably what brings the cells together. We can, under these conditions, interestingly, do co-cultures of cell types, different cell types, that will otherwise, in, say, flat culture regularly on a tea flask or something, one would prevail over the other, and you don't get a good harmonious relationship between them. So the other thing I think that's really important in the context of the tissue engineering side of this is the freedom for three-dimensional replication rather than in 2 dimensions that's in a gravity-based system. So these cells actually have the opportunity to replicate in 3 dimensions and give you more like a tissue construct. And the other thing about it is that it gives you a new sense of control for the physical force environment. And Craig talked to you about all those things that happen as a consequence of gravity, and those things, when gravity is diminished, that disappear. But what we didn't say there, and what we'll say now, is that probably brings a system now that has a new priority for the influences of forces on life, the remaining forces that are there. And so I'll take a quick look at that in a few minutes. But the primary requirements for engineering a tissue, you've got to have a cell source that can proliferate and differentiate. You also need scaffolding materials for some of these. Now, some you don't. I said scaffolding materials here. And a lot of these are synthetic scaffolding materials that have been very cleverly designed with the right kinds of chemical subgroupings on them for the interaction of cells. A bioreactor is an important aspect of this. And how do you maintain a physiologically balanced system to actually grow tissue instead of just growing cells? And that in itself is a challenge, and we'll touch on that just a little bit. And then whether or not in these instances do you need a real battery of specific growth factors and things to be added to it to actually induce the desired effect that you want. In some instances, believe it or not, the cells will do these de facto on their own if they're given the appropriate environment. So the kind of milestones that we looked at in working tissue engineering in the microgravity setting, we picked 5. I mean, you probably have your favorite. There are probably a lot more things you'd like to see on this chart, and I'm sure you'll be ready to tell me what I left out, and I'm more than happy to accept that there are a lot of things left out. But assembly is one of the most important contributions that microgravity gives you, and that free assembly that we were talking about before, that agglomeration that takes place, and the 3D growth. And what we see consequential to that is a de novo synthesis of matrix material. And that is critically important because that's a native matrix. Okay, so we're not looking at something that's necessarily artificial in all cases. Sometimes we do use artificial matrices in these. And consequential to that is that the appropriate signals are then provided for some differentiational events to take place that otherwise might have needed to be induced externally. And lastly, you know, as the tissue grows in size, and I mean, Dr. Folkman, Judah Folkman, I think clearly stated you're about more than about 100 microns from a capillary, the cell's going to be dying. It's going to be going away from you. And so as these tissue assemblies get larger, we've got to have ways in which we can deliver it. And I can tell you that based on the space tissue engineering experiments that have been done so far and what's been done in analog on the ground, and I'll explain that in a second, 4 of the 5 of those are clearly achievable. I think vascularization is another story entirely. We can discuss that afterwards. You look at scaffolding materials, and I already talked about what these scaffolding materials is, and one that's not on this list that's pretty important is the decellularized native scaffolding material. And for those of you who aren't familiar with that, you can remove all the cells from an organ, like a kidney or from the liver in particular, and leave just the remaining scaffolding material matrix, and you can repopulate it. And the good part about that is that it gives you some sense of dimension for what the organ might be and whether or not you can actually do that. And the second thing, I guess, about it is if there's any hope for transplant, we're probably going to have to be able to have something that's reasonably ready to be anastomosed into the vascular system and whatever systems, other systems that have to be accommodated. There are some limitations when you're looking at this. It's obviously tissue size is limited by the transport of nutrients, mass transfer. And in microgravity, it's an interesting property. If you took a cell, put it in a jug of media and take it to space, and it's just hanging in there in the middle of that, the theoretical aspect of its relationship with its environment would tell us that it would assimilate oxygen and glucose at a much faster rate than it can diffuse, and thereby it would actually eat itself into a zone of depletion. And it would no longer be fed, like it is on the ground, by buoyant density-driven convection. That's what's happening in your cultures in the incubator every day. It would not be fed by that. It would be fed literally by fixed law. Okay? The rate of diffusion would determine it. And so the question was, would the cell survive or wouldn't it survive? And interestingly, they do survive. Many of them do survive under those conditions and adapt. So when you're looking at a cell adapting to a space environment, you can't immediately say, oh, this is the response to microgravity. It's really a response to being fed by fixed law, which we can actually rig on the ground here. It's not necessary. So we don't know if a cell has a gravimeter in it or not. We know that tomato root hair cells do. Okay? And those kind of things have gravasensors. But most of the cells in the body, we don't know for sure if there is really a gravasensor there. So I'm going to skip this. This has to do with the thickness of the tissue, and we're looking at the time, and I don't want to get into trouble here with it. One of the things that was decided in the early phases of the tissue engineering in the space program is, what cells to go for, and we went for cartilage. And the reason we went for cartilage, we consider them our astronaut cells. Okay, these are the right stuff kind of thing, because they have very few demands on their culture system. They're very easy to get along with, and they can take a lot of punishment. And so that's why it was done. And when we looked at these, we looked for key production of very specific evidence of their differentiation and propagation. And that's listed there, those characteristics, and you're familiar with collagen. The first place we do this is in an analog culture system. An analog is not a simulator. An analog shares some of the characteristics of the real situation. Okay, for the cancer folks here, this is like B16 melanoma and C57 black mice, and we're really trying to understand how to manage melanoma in human beings. It's neither one, and it's not really a simulator, but it's a good analog because it shares enough characteristics that it can inform us. And that's what this does. This informs us. And so we use this system. It's a rotating cylinder. It looks to you like a roller bottle culture. It is not, because it's completely filled with fluid. All the way. It's a zero headspace. The way it gets oxygenated is down the center on this cylinder that's inside there is actually a gas permeable membrane that allows oxygen exchange and carbon dioxide dissipation. Important thing is once you start rotating this, the fluid rotates with it. That's a concept you have to remember. It's rotating along with it. It's like it's called viscously coupled. It's like it's a piece of that rotating cylinder now. And cells being slightly greater in density will then sediment, and they continue to sediment, okay, with very few wall impacts if you adjust the rotation correctly. So those are cells that are in free fall. They're actually falling at terminal velocity in the fluid. So it's kind of like being on the parabolic airplane that they use to simulate microgravity for training called the Vomit Comet. All right, everybody, you know, so it's kind of like being on that, only they never pull out. So this is the analog system. This is cartilage that was grown in the analog system. If you look at the center line on this, this is what it looks like histochemically, and it's what you would expect to see. There's native cartilage, and it's got the lacunae, and it's got differentiated chondrocytes. And when you analyze this matrix, it has all the chemical properties that you would expect to see. It said chemical properties: type 2 collagen, alkaline phosphatase, glycosaminoglycans, and that kind of thing, which you would expect to see. They're there. What doesn't it have? It does not have the same compression modulus that a piece of cartilage on the ground would have. Okay, so it's a lot softer. And when we show you the space, when we show you what happens with that. This is in standard stationary culture. These are all perichondrial cells without any evidence or very little evidence of any kind of differentiation that takes place. So in that analog system, you could actually get some of the things you're expecting and wanting to see out of the space. And this is some of the properties that you see in these engineered cartilage. And I think I just said what they are, so I don't think you need to go into it. It just tells you that these particular components we were talking about, type 2 collagen, glycosaminoglycan, and those kind of things, are in specific abundance. And to identify that it's actually type 2 collagen that's actually there and being expressed. And that's what we see under these are the controls, obviously, and we're looking at native cartilage versus engineered cartilage. And I think you can see there's reasonable parity with regard to the components. And now it comes time to do an experiment in space. Life ceases to become simple because you can go to the incubator, you can tweak the cells, you can give them some media, you can do all these things to them, you can mess around, you can take a look at it. This has got to operate on its own. Everybody's on its own when you go to space, and that's what made cartilage a very good thing to do this with. This is a device that will do it. This is a rotating bioreactor, and for those of you who need a discussion on why we rotate anything in space, I'll have to give you a different level of discussion on it, because it is not centrifuging those cells to the side, and they are not experiencing more gravitational forces. It's an interesting property that takes place. It's done in this regime like this for mass transfer. If we don't get sufficient mass transfer for the cells to survive. And the way this was done is that these matrix constructs were populated with perichondrial cells and then put into either flight or control rotating systems on the ground. And what we found is that, yes, indeed, they will propagate. Yes, they do differentiate. And yes, they do grow and into a tissue assembly. Everything that was on the ground in the rotating system on the ground ended up just like a hockey puck, like that disc that this was to start with. It grew to the dimensions of the matrix. We talked about how important the matrix is. Here you can see in space, it actually grew outside the matrix and beyond. And all the constructs that we got back were spherical, which is a very, very unexpected and unusual finding. And so when we looked at these histochemically in trichrome, this is what they look like in space. There they are there. You can see the balls. They hang over to that one side for a very specific reason. It's attributed to the physics of the inside and how it's designed for mass transfer. But this is what we would see from the space. And both of them have just what you would expect to see with regard to their morphological properties. And so everything is fine here. The biggest difference is that these are mechanically so weak that it was incredible. And the reason is they're totally unloaded. Okay, cartilage on the ground is loaded, and that's one of the properties that's necessary during chondrogenesis, is to have load. So these are completely unloaded, and because they're completely unloaded, they are very immature and mechanically inferior to what would come out of a ground-based system or come out of native cartilage. Now, is that bad news or good news? Well, the good news about it is that when you put these into a transplant model in rabbits, actually the more compressible cartilage remodels against the existing cartilage, right, much better than more mature cartilage. So it may be an advantage that, for the purpose of which right now we don't really understand why that happens, but it does happen. We've grown other cells in this to grow actually three-dimensional tissues, and proximal tubule cells of the kidney were chosen for a number of reasons, because they have particular properties that we wanted to be able to see if whether or not we could actually get them to differentiate and express those properties. And one was, robust presentation of microvilli, secretion of erythropoietin, and then the production of 1,25-dihydroxyvitamin D3, and then these two receptors, cubolin and megalin, which are important in the response to aminoglycosides, something that we get concerned about in patients being given high doses of those kinds of antibiotics. And then the gene expression changes. When this experiment was done, it was a surprise to us to see it in proximal tubule cells that when we put these together, co-cultured them with the mesenchymal component that we had isolated from kidney. Right? When you keep that mesenchymal component out, you don't get, what happened? Oh, okay. Just do the same thing again, it'll come back. This is without the mesenchymal component. This is with the mesenchymal component. And you can see here the robustness that I was talking about with regard to the microvilli formation and the fact that there looks to be like a lot of differentiated cells there. And so what that did was give us a basis on which we then knew that we could get, and we did get, erythropoietin and some others from it. This has flown, and it's not in here, but I can get you the references or provide for you the reference showing you the illustration, where they actually looked at the gene expression on a chip array with 10,000 genes. And the important thing here to know is that in microgravity, about 1,600 out of 10,000 genes were upregulated or downregulated more than 2 logs off the normal axis on that. And that was quite a surprise to us, because normally with any kind of physical stimuli that we've been looking at, like hydrodynamic shear, even hypergravity, you have a response suite that's there. Temperature, the heat shock proteins, what we call it originally, that shock response has got a refined set. There is no refined set when we go to microgravity. And there's probably a good reason, right? The good reason is that you've never had to adapt. Life has never had to adapt on this planet to a diminution in gravity that's sustained. That acceleration has been 9.8 meters per second squared for the entire 4.8 billion years of the planet. So it is a constant in the development of life. It has never been a selective pressure. And so this will be very interesting as we transition life and life systems to microgravity to look and see which amongst all of those, that morass of changes that occurs, is actually essential to the adaptive phase and how the cell responds to this. And so that's something we haven't sorted out, and it's a future for somebody who can write a good grant and go do that. I'm going to show one or two. Actually, I'm going to skip this. This is heart muscle, and it works very, very fine. I just wanted to show this is an engineered piece of heart tissue. This was from individual cells that were allowed to reassemble under the analog conditions. And you can see that all the various components that you would expect to find in mature cardiac tissue reform and put themselves together. Not exactly in the right order, in the right places for everything, but it's just quite amazing that even the adrenergic component is preserved. Okay, and so because it is preserved, these cells will actually, so I'm going to do this from here. If I screw this up, it's like my kids. It's not my fault. Actually, my grandkids. But in any event, you can see that the contractile activity. Now, what you're seeing here is there are two strands of cardiac tissue engineered from individual cells that happen to be aligned across from each other. And it's kind of like a Moyer pattern is, because they're got those striations in them. And as it's going, that's why you see that movement that occurs there. But you can actually preserve and reestablish that particular set of characteristics in it. And there are a number of interesting things about cardiac tissue that's done that way. They have a higher excitation threshold. That's no surprise. This is heart muscle that was never really loaded. So it's going to take a lot more to kick it into action. So nothing there is a real surprise. It's just as far as the physiological things. I want to talk about one thing. The models that you can do under these conditions for infectious disease, endometriosis, liver function disorders, endocrine dysfunction, parasitic infestation, all of those have been done using this kind of model. We'll not go there. I'm going to skip the colon carcinoma one because it has been successfully engineered under these conditions. I want to show you this one. This one was on Columbia, unfortunately. And this was prostate cancer that was put together with bone marrow stromal cells. And we all know that with these epithelial tumors, that when they metastasize to the bone, that's when things become intractable. So we know there's a special relationship between the two. And the idea behind this experiment was to be able to create a tissue construct that would allow us to actually study that property. And Dr. Leland Chung, who was at Emory at the time, he's no longer there, is the one who did this. And so this is a ground-based bioreactor on the ground down here. And this is one in space. You'll notice the one in space moves much, much slower. The color difference is mainly because of the lighting that's up there. But if you look, you can see this granular array of tissue constructs that are forming under those conditions. But in the space, if you look closely, you will see that there are these large assemblies that have formed, and they produce a number of the characteristics you would expect to see from prostate, not the least of which is PSA. And it was a first opportunity to start to look at that relationship, and we are looking forward to the day when we can actually get back to doing that. So that's pretty much what I wanted to say today. This is the shopping list of all the cells that have been put through this, either in the analog state or in space, and they're separated out for you. What's been done in space and what's been done elsewhere in the analog system. And I think you can see that we're setting the stage now for hopefully having enough seminal information for creative minds to start to propose on how they would use the physical environment that's unique about space to answer some really important biological questions. And with that, I'm going to stop and say thanks a bunch for inviting me. I really, really appreciate the opportunity to do this.
Okay, so we do have time for a few questions. Tim?
So I'm interested in what you presented. It almost looks like stem cell biology. It's sort of saying there in talk. Are your tissues growing out of stem cells, or is this just a microgravity effect on the tissue?
The question is, are these growing out of stem cells, or is this an opportunity that the existing cells are taking to actually grow out, to undergo tissue morphogenesis? We cannot identify anything in a way that's due to a very pluripotent stem cell in these. It doesn't mean that they aren't there, but I think that what we're seeing much of here are just the cells themselves, differentiated cells themselves, whether they're retro or whatever, to be able to replicate enough. Because if they're fully differentiated, a lot of them won't replicate. But it seems like we get replication out of it. But if it is a stem cell, it's probably more much further down the line than a pluripotent. And I hope I'm out of trouble on that, Carol.
Yes.
You want to know what happens to the cells when you come back, you bring them back, these tissue assemblies. And a lot of these tissue assemblies are pretty flimsy. And so when you bring them back, they will actually dish back out on you. We don't do that a whole lot. Usually those things are preserved and then they go on for analyses. And so we don't let a lot of them go to that. But I think some of the more mature things, like some of the cartilage that had been, that cartilage, by the way, the construct you saw, is the longest continuous cell culture in space history, 137 days. They were, even though they were mechanically inferior, they're quite robust.
So let me ask this question in terms of, since you mentioned the change in gene expression with 1,600 genes being either up twofold or down twofold, is there any difference in signal transduction within cells there? So when you challenge the cell with the stimulus, either the signaling going to the nucleus or up to, let's say, RNA expression or protein expression, does that change any?
Yes, sir. There are substantial changes in signal transduction along specific pathways. If you lost all signal transduction, they would die. Yeah. But it's interesting, we look at lymphocytes and the signal transductional events that involve the pathway through protein kinase C seem to have some significant impairment. And so how it happens, how does it change signal transduction? It doesn't look like it's ligand-receptor interaction that's interfered with. It looks like it's a transductional event that's right at the membrane. And as we back up through the various stages and looking at it, we could see that it may be a stage where phosphorylation is actually the impeding event. The absence of phosphorylating certain enzymes seems to be the... Now, so how does that occur? Well, there, you got the cytoskeleton and the membrane and focal adhesion complexes and their like, okay, that have got this tense network put together, and you've now taken them to microgravity. And when the cells go to microgravity, the first thing they do, just like you have cephalid fluid shift in humans, they actually reduce their surface area to volume ratio. They become round. And in doing so, it's believed that they displace certain enzyme substrate geography, okay, and thereby not getting things phosphorylated the way you would expect.
Okay. Well, thank you. And I'm going to hold my question on chondrocytes till the break, okay? So be ready. So now it's my pleasure to be able to introduce you Carol Brenner. Dr. Brenner is the Associate Dean for Biomedical Affairs and Research here at the VCOM. Dr. Brenner received her Ph.D. from Tufts University in Boston. She has been involved in higher education for over 20 years. She has done and published research on all kinds of fields in terms of reproduction, in terms of mitochondria, in terms of mitosis, but she's really developed a big interest in stem cell biology, and that is one of the really, truly remarkable turns that science is taking now, that the stem cells will be able to help in so many ways, whether you're talking about understanding cancer from cancer stem cells, and here we're talking about many times adult stem cell tissues. So she will be presenting a talk on the promise of stem cell research. Carol?
I'm going to start a little bit on the historical aspect of stem cells. And interestingly enough, I'm going to end where bioreactors and potentially cancer stem cells can actually be utilized in novel systems, and nobody's actually done that. So in a sense, I'm going to go backwards, and then I'm going to end where you actually ended also. And specifically because we haven't really done any stem cell biology in South Carolina, I thought I would give you an historical perspective of really where we started stem cell work. So initially, without doing human embryonic stem cells or not knowing anything about human embryos, we had to start from the beginning. Oops. Why is it doing that? So I always like to have learning objectives for our students. So we do have some learning objectives, and you'll be tested at the end of the lecture. Okay. But I'm going to tell you a little bit about what we talk about. What is a pluripotent stem cell? Then we're going to actually talk about what is an embryonic stem cell, and we are going to talk about how we have been able to actually reprogram adult cells like skin and blood into stem cells called induced pluripotent stem cells. Then I'm going to review a little bit of the data that I've actually published and end up with some of the clinical trials that are actually being done in the U.S. right now. And they're very, very exciting results from both the U.S. and Japan, and actually you can actually replace what we call retinal epithelial cells, and it's actually restoring vision in patients that have a early form of macular degeneration. So we're really moving very, very quickly now from where we started, and this year actually is considered to be 2013, the year of when induced pluripotent stem cells are really going to be used for personalized medicine and clinical trials. So it's always important to know that when we're talking about stem cells, we're talking about their differentiation potential. So when we're talking about differentiation potential, we're talking about something called totipotent or pluripotent, unipotent, and multipotent. So it was actually thought, so when we actually isolate the inner cell mass from the structure called the blastocyst, we did know, and we always have known, that actually it can produce every cell in the body. But what we did not know is that if we took an adult stem cell, that we could actually reprogram that back into what we call a totipotent state. That has really been the paradigm shift in stem cell biology in the last 2 years. So the place I'm going to start is really where we should start. I had the pleasure of working with Bob Edwards, and Bob Edwards got the Nobel Prize in 2010, and he was the first one to show that you could actually grow embryos and replace them back into a patient and produce a baby. So this was the whole development of what we call in vitro fertilization field. And this is something that actually started in the 60s, and yet Bob Edwards did not get the Nobel Prize to 2010. One of his graduate students, Barry Bavister, played a key role in this, and Barry actually was the first one to show with a simple change in the pH and culture conditions that you could actually take a sperm and fertilize an egg. This had not been done in vitro, and this was actually a turning point, because without being able to do this in an in vitro system, we could not actually have then grown the embryos in vitro culture and produce all the babies. So here, actually, this is Bob Edwards, and this is Barry Bavister. And the reason I mention them is I've had the opportunity to work with Bob Edwards, and then Barry. I'm going to show a lot of data that Barry and I generated up until 2012. And this is Barry when he made the first discovery with Bob Edwards, so that they could actually see that a sperm could inseminate an oocyte. So that's a 1969 Nature paper, and presently there are over 5 million babies that have actually been produced by IVF. Sadly, I will say, well, I guess, okay. Now the other thing was, because of the ethical issues with human embryonic cells, we actually developed a non-human primate model. So in order to be NIH funded, we could not work with human embryos. So Barry at the University of Wisconsin actually developed the first monkey by human IVF, and he called the monkey, this is Petrie, the first monkey in a macaque monkey, and this was done in 1985. And the reason this was important too is because Wisconsin had a unique culture. And not only was Barry there, but Jamie Thompson was also there. And Jamie Thompson is actually known for producing the first human embryonic stem cell culture. But what many people don't know is actually Jamie, the first time he did this was actually in monkeys. So using NIH money, the first actual, in 1995, he actually successfully isolated and cultured rhesus monkey embryonic stem cells. And what he could not do was he could not actually culture these in vitro. So he actually flushed the embryos from the uterus, and he made a series of embryonic stem cell lines, and we called them in vivo embryonic stem cell lines. It is this point that actually, now interestingly, Barry was very involved with the culture of some of these embryonic stem cells, and he was also actually involved with, some of the first human stem cells that they grew at University of Wisconsin, but they could not use NIH funds. They had to use private funds. But again, when we talk about the beginning of stem cell biology, what we have to do is talk about what's very interesting, the culture of the lab and who's in the lab and how people actually are enthusiastic and work together really is what produces breakthroughs in science. And again, I think that's important because I think that that's what we're trying to do at the Gibbs. At the Gibbs, if we have that kind of environment, we hope that this is the type of place that we can see some breakthroughs in, for example, cancer stem cells. So that's why I bring this up. And again, some of the work that I got funded was because I actually worked both with Barry, who originally worked with Bob Edwards, and then Barry worked with Jamie Thompson, and then Jamie Thompson actually gave me his in vitro monkey stem cells so I can compare them to in vivo to look at whether we really know how to make stem cells that actually can be used for therapeutic medicine. So here's our first test tube monkey, and this is Petrie again. This was at Wisconsin National Primate Center, and then Jamie is still there, and now there's a huge embryonic and now iPS stem cell production. University of Wisconsin has some of the largest funds now to do regenerative medicine in stem cells. So I'm just showing you here that when we started working with monkeys, we actually had to show that we could do the same things in monkeys that were done in human IVF. And this is to point out it's the inner cell mass of the blastocysts that we were able to take out and actually make into embryonic stem cells. But these are in monkey now. They're not human. These are monkey embryonic stem cell lines. So in collaboration with, so this is actually showing that the development in rhesus macaque it develops very similar to human embryos. And so here we can see a one cell. This is actually a fertilized egg. So here you can see the male and female pronuclei, a 2-cell, 4-cell, this morula and compacted morula, and here's a blastocyst. So if I took this and compared it to a human, how human embryos look, you could not tell the difference at all. So it's this group of cells that we use to make the embryonic stem cell lines. So here we show again in how we actually produced some of the in vitro embryonic stem cell lines. And what we used here, again, this is the monkey. We actually used immunosurgery, and we cultured these inner cell mass on a feeder layer, and we were able to produce monkey ES cells. Now, the question we had was whether in vitro monkey ES cells are similar to the in vivo monkey embryonic stem cells that were actually produced. These were the first lines that actually Jamie Thompson produced. And again, I'm going to skip that, but what we've done is we've actually looked at the genetics in non-human primates. So here's all of the cell lines that we've actually produced in vitro, and this was done in collaboration with Oregon Primate Center. Primate centers did do a lot of collaborations because there are not many U.S. primate centers, and so many things we did. And so what we have shown now is that you can look at the lines and they look very similar, but when we actually do the analysis and we look at the whole genome and we actually look at the epigenetics, we just finally published this paper. And it took a long time because there weren't monkey arrays and there wasn't a lot, we didn't have a lot of resources. So NIH had to put a lot of resources in to help us do this work in monkey. But the take-home message really is that in vivo produced monkey embryonic stem cell lines are very, very different than in vivo produced. In vitro produced. So this brings up a lot of questions about culture stem cells, and we're not really there yet, but we hear a lot about that, and we have to think very seriously about that if we're going to make these lines for regenerative medicine. So that's our take-home message there. Now, the paradigm shift was, and this Yamanaka and Gurdon just got the Nobel Prize for making what we call induced pluripotent stem cells. And this Nobel Prize was actually given in 2012, which is only last year. So you can see in terms of Nobel Prize, the gap between when Bob Edwards got the Nobel Prize and Yamanaka got the Nobel Prize is only 2 years. So Bob, after many, many years and 5 million babies, really was the founder of what we call the stem cell field, because without producing embryos in vitro, we would not be in this place in stem cell biology. And the reason this was a paradigm shift is because, and the reason they got a Nobel Prize, and there's a lot of discussion why Jamie Thompson didn't get the Nobel Prize, was that they took 4 genes that are transcription factors that are found in pluripotent embryos. And they actually forced them by using lentiviruses, and I have a lot of pictures in the next couple of slides, and what they were able to do was to reprogram these adult cells into pluripotent stem cells, and they look just like embryonic stem cells. This is a paradigm shift. We never thought that we could actually do this, and the first hints that we could actually do this is when, if you remember the cloning era, when Dolly was born. So Dolly was actually born using nuclear transfer type experiments, but they used a somatic cell and they actually enucleated the inner cell mass, and out of that came the first cloned animal, and that was Dolly. But we all knew that this was never going to work for regenerative medicine because of the fact the truth of the matter is, in order for us to proceed you're going to have to take the cells from the actual patient and grow them into specific tissues, and because there's a lot of problems with immunological compatibility. So this is why this was considered a paradigm shift, and in some level a lot of people have asked, why was this so simple? Because only the 4 major genes that are the major pathways for pluripotency were actually inserted into the normal cells. So this has had enormous impact on the field. So now we have the possibility of generating patient-specific stem cell lines. We can actually use this to study the mechanism of different diseases. We can use this to look at drug discovery and toxic effects. And it actually has altered the debate now, because people were very worried about using human embryos for ethical reasons, and now pretty much most stem cell biologists have completely shifted to this type of technology, and this is the type of work we actually will be doing at the Gibbs Center. We actually will be reprogramming specific cells. We can use skin, we can use red blood cells. Actually, I can pull my hair, and actually I can grow stem cells right from the follicle of my hair. So don't let me pull any of your hair. Okay. So we knew that nuclear transfer was not going to be the way that we could proceed in regenerative medicine. So here you can see, and this is Dolly the sheep, showing that, again, slight paradigm shift, that we actually could reprogram using somatic cells, produce Dolly, but we knew that nuclear transfer was not going to be the way for us to proceed in regenerative medicine. So what you see here is a big X. So this is really our model now, and this is really the model for everybody. So we can by taking skin cells, we can actually force these cells to be reprogrammed, and these are our reprogramming transcription factors, and these again were the major genes that were in the inner cell mass of the embryo. So these are our 4 genes that we reprogram with. And these are KLF4, OCT4, c-MYC, and SOX2. We're now taking c-MYC out of the mix because c-MYC is actually an oncogene, not a great thing. These are actually force-fed lentiviruses, not a great thing if you're thinking about regenerative tissue, but indeed many people are still using this lentivirus approach because it generates stem cells very quickly. Very hard to force these cells to actually reprogram. Only about 1% of the cells actually reprogram. And in the beginning, it was taking 3-4 months to actually reprogram the cells back because you actually have to change the complete epigenetics of the skin cells. So our paradigm shift is that now we will be able to use these skin cells or red blood cells or even hair follicles from patients to actually regenerate many types of tissues. So this is where we are with this. But again, a lot of people are still concerned about whether even the induced pluripotent stem cells, because we haven't really found a safe method now to reprogram yet, whether they're actually going to be the stem cells for personalized medicine. But there's been some recent articles that have actually shown that when you transplant tissues, and this is a mouse, that have been generated from induced pluripotent stem cells, that the cancers are not formed. So this is a very big concern of this whole area. And so one of the questions we have is, how can we do safe reprogramming? And this is something that I started working on when I was at Wayne State. And one of the ways we can think about what we call safe reprogramming is to look at populations of cells that are stem cells but actually really exist in nature. And So I was at Wayne State. I started to work with the perinatal branch, and we started to actually take out, so amniotic fluid was, the hypothesis is amniotic fluid doesn't have stem cell populations. So we started to look at what percent of amniotic fluid actually has stem cell populations. And the reason that's important is that, you know, it's a terminal fluid, and again, it had the potential. I'm going to have to go through this very quickly, but again, this is very important because this is something that I think that as we go through some of the things that we talk about in cancer stem cells, so we did some experiments and we found very quickly that we can reprogram very quickly using amniotic stem cells because they're partially reprogrammed. In other words, some of the stem cells actually exist in the fluids, and we actually did some cell sorting, and we found that certain populations contained more stem cells, and even though they look like this, we did find that the c-kit fraction actually had many more stem cells than the normal AF cells, and we picked cells. We made about 60 lines, and we characterized them, and we showed that they look just like iPS cells from any other source, such as skin. So I'll go through that quickly. And the other thing we did find is, unlike other stem cells, these cells do not cause immune reactions. They're very specific. You know, again, this is a specific area. We don't reject our babies, and amniotic stem cells actually have properties that actually can be used for universal stem cells. And the other thing is, this is actually the material that Atala up the road at Wake Forest is using to, when he creates the scaffolds, he populates them with the amniotic fluid. So there is a better population. Now, the other thing that the field is doing now is they're really looking at disease models, and there have been a lot of disease iPS cells created, and here's a list. But one of the things that's very important is you have to actually make banks, because you can't just look at one patient for the development of personalized drugs. So they sell one of many, but I can tell you right now, all the banks are being developed, and they have a lot of IP, intellectual property, and now they're being used for drug development. We got funded to actually make stem cells, a bank of stem cells from amniotic fluid, because there were rare perinatal diseases that don't exist in any other stem cell area. So that was the last thing that I actually did at Wayne State before I came here. And unfortunately, because the perinatal branch is NIH, it was determined all of those lines had to stay with NIH. So I don't have any of those lines anymore. One of the areas right now that is very exciting is the treatment for retinal disease. And this is Robert Lanza, and he's at a company called Advanced Cell Technology. And he's been doing testing with retinal epithelial cells, placing them back into the eye. And he's actually doing safety studies right now. But in the process, what he has said, and actually I was at a meeting 2 weeks ago, and what he told me is that actually in some patients with some of these diseases, some of the patients are actually having their vision is actually being restored. So they actually have found that they are safe. They're going into another clinical phase. And in some of the patients, their vision has actually been restored. And so this area is very hot now. You know, this is like the hottest area in stem cells right now, because this is a patient that had was legally blind, and then a week after treatment, she could actually count her fingers and see her computer. And these are the structure of the retina. And what we're talking about here is actually replacing the retinal epithelial layer. But now people want to start, they actually can make photoreceptors in culture. So then the question now is, can we actually replace those cells for treating things that are involved where we have retinal problems. Okay, so this will actually bring us to treating both an animal, well, the animal studies worked, and there are actually over 200 retinal diseases that actually can be cured using now iPS cell type of work. Originally he started with the embryonic stem cells, but now he knows that the iPS route can actually cure many of these retinal diseases. And, you know, as you go through my slides, you can look back how these things are actually done. But I want to get to the end, which is where we talked in the last talk. And one of the biggest areas in stem cells now is scaffolds and stem cells. People know that you know, this is very unusual that you can actually inject cells without any scaffold and see improvement in the eyes. We won't be able to do that in many other systems. So one of the projects we've actually started with Clemson is actually doing what we call an improved reactor control for stem cell expansion to meet the therapeutic needs. And this is part of a COBRA, the Center of Biomaterials for Tissue Engineering. This is one of the partners I want to bring in to our Gibbs group, because there are many things that we may be able to do to work on cancer stem cells using some of the bioengineering types of things. Again, she showed that with a specific type of mesenchymal cell, that in these bioreactors, you're actually expanding these cells exponentially from different cell types. And interestingly, we've gone back to the work that we did with Barry, and we're finding that it's actually pH and low oxygen that are really growing these cells exponentially. And the next phase of these experiments is actually to create iPS cells and put them in the bioreactor and look to see if they expand. Because one of the biggest problems we have in iPS as the initial tool, or in even differentiated cells, is to make a large amount of cells. This is where the field is really in crisis in order for us to move to actual a lot of trials. We cannot grow a large amount of cells. And this was our specific aims, improve iPS reprogramming, and we have an improved control bioreactor, and the first part is actually to make red blood cells, but from red blood cells you can make things like platelets. Now we can actually look at this as a potential way to utilize the system that we just talked about. The interesting thing about embryos is the inner cell mass is actually a very interesting cell type. It's metabolically inactive. It doesn't need oxygen to proliferate. Needs very, very low oxygen. In fact, it's thought that maybe we don't need oxygen at all, and that the only way that it sits in the embryo in such a way that it probably can grow better in some type of microgravity situation. So one of the things that I think would be very interesting for us is to explore how we could make large amounts of cells using bioreactors and make large amounts of iPS cells. I think this actually could be very conducive using scaffolds and specific microenvironment conditions to see if we could actually sort out some of the cancer stem cells and look to see which populations are metastatic and which populations are truly pluripotent, because there is a progression where the stem cells in the cancer are not, they aren't forming cancer. So there's a process where they go from pluripotency to metastatic growth. And this is the big paradigm shift now, I think, in the cancer field, because it was thought for a very long time that there weren't cancer stem cells. It's very clear now there are cancer stem cells, and these may be the cells that we can't hit with many of the therapeutic drugs, and that this is the residual population that causes metastasis in breast cancer, colon cancer, pancreatic cancer. So the point of all of this is, with novel bioengineering, novel types of things like microgravity, two wonderful people who are very smart and my stem cell background and other collaborators, what can we do that will be very novel for our Gibbs Center, VCOM Gibbs Center? And I think that we do have the right microenvironment to actually do some amazing things. So with that, I'd like to end.
So we're lined up, and don't leave now for a break. So we have a little bit of extra. I can sort of push it a couple minutes, maybe for a question or two, if we have any questions. Now, do you find that, or is it sort of found that the adult stem cells that one can isolate out of marrow, they completely recapitulate the embryonic stem cells? There's always the argument that, well, they're not quite pluripotent enough.
And that's still the big issue. I mean, the question really is the epigenetics the same as the embryonic origin? And I think, again, there's certain populations of the iPS cells that can capitulate and are important for regeneration. And some of the things that we have to do is be able to separate those cells. And again, with novel scaffolding, bioengineering ideas, and bioreactors, these are types of things that we're moving towards. Yeah.
Tim?
Carol, we heard the other day from a colleague in the Mayo Clinic that there's certain trials going on now. There's a phase 1 trial called the CASIS in cardiology, where cells are isolated from bone marrow, translated to myocytes, and injected into the heart. Patients that have had heart attack because of heart failure, they actually see pretty good results and ready to go to phase 2. Are there other trials like that?
Well, actually, the trial that I was showing you is actually one of the most successful trials, and that's with the ACT and Lanza. But in the heart, there's been a lot of controversy whether injecting the iPS, the stem cells that way, are actually going to be really restore cardiac function, because many people feel that there has to be some scaffolding, and the cells have to be actually sewn into the heart, because when you have a large part of the cells actually die when a person has a heart attack. So the jury is out whether that technique is actually going to work. I think many scientists really feel it's the scaffolds that are really going to help with heart repair in the end.
Dr. Bearden?
Carol, I wanted to ask you about the state of cartilage regeneration. I know there's been a lot of, I suppose, commercial interest in that, to regenerate cartilage, damage to meniscus and others. Where is that right now? That's a lot of published data.
Well, actually, that field is going like gangbusters with the bioengineering group. And again, that's not my specific area, but I will be attending the Clemson group. The Clemson group has actually done a lot, but so has a lot of the tissue engineering groups. And in Georgia actually has a wonderful group of public and private universities that have come together to actually do many of these things. And again, what we're seeing in stem cell biology, it's really the collaborations and consortiums that are really pushing the field. So that field is actually moving quite rapidly now, and certainly we could get a speaker to come in to talk to us about that. Well, the closest human clinical trial I'm giving, I switched to the situation where we're looking at curing eye disease. That's our closest clinical trial right now in the U.S. That's actually working. And so that's why I switched to really, I gave you the end part. This is the one that's really moving the fastest right now, and we're in a race with Japan to see who's going to win. So just so you know.
One last question.
Would you comment on nerve tissue regeneration, where we are with that?
Yeah. Now, actually, nerve tissue generation, iPS cells, no stem cells the same. But we actually have found when we reprogram cells into iPS cells, their default pathway is actually more in the neural area. And so there really is great hope right now that the reprogrammed stem cells that were growing into different types of neural lineages are going to be very useful very quickly. So the state of the art right now is that many people are actually rapidly making stem cells from every type of neural disease that you can think of. I mean, autism, schizophrenia, you name it, it's happening right now. And the question there is they're still using the lentivirus for doing drug testing in pharma, but it still has to be backtracked into how to make safe cells for transplantation.
Yes, lentiviruses are difficult to use, believe me, I know. So that's good. But I want to say that, let me just add to this that, you know, the research that we're talking about today in all these areas, it is just, you just don't know where the breakthroughs are going to come. You know, my parents told me 50 years ago, President Kennedy announced that we were going to the moon. And a lot of people kept wondering what we're going to, why we were doing that. And it seems like a pittance that they spent to do it. But the amount of technology, I mean, the fact that you can sit there and not have to listen to a thing, just texting, all this electronics, you know, Microsoft, Apple, that all stems from that original moonshot. So it's amazing what's going to come out of here. One of the things that Carol mentioned I think is really fantastic. She talked about the protection on that one cell. I think it was probably the green cell, that embryos can protect themselves from the immune system. You know, it was only a week and a half ago that Dr. Weissman out in California announced that CD47 is the thing on the cell surface that says, "Leave me alone, immune system. Don't eat me." He called it the "don't eat me" gene. Well, it turns out cancer cells can make that. So your immune system doesn't attack them because it goes, "Oh, look, they're developing this nice little baby in this person's liver." And that's not what it's about. And he has an antibody to block that. And his work shows that it's having some stellar effects. So these things, it's going to pop up and really be some exciting stuff coming up. All right, so I think we can go ahead and get started with the rest of the program. I've been really delighted to hear your comments about the first part of the meeting today, and I agree completely with what I've been told by various people that are in attendance, just the interest in learning the things that we have learned. And I still, once again, really want us to continue to look at how this can fit together in terms of a model for delivering personalized medicine for cancer. Now, our next speaker is going to be by Dr. Ed Fleming. Now, let me tell you that Ed is with McKinsey and Company in Silicon Valley out in California, and he joined that company in 1997. Now, the most interesting thing about my introduction of Ed will be right at the end of the introduction. But let me just tell you that he received his bachelor's degree from Harvard, and then he went to Vanderbilt. I'm not sure he was at Vanderbilt at the same time I was there. But then he went to Johns Hopkins for internal medicine, then to the University of California at San Francisco for pulmonary and emergency medicine training. And so one of the things about Dr. Fleming that I did not know until just last week when Dr. Bearden came to my office, that Ed is from Spartanburg. And his sister is the president of Converse College here. She was planning on being here today, but Tim put this meeting on the same day as her board meeting, and she couldn't attend. But also Ed's brother, who I'm sure many of you physicians know, practices medicine here in the upstate area. And Ed's here to talk to us about personalized medicine, the state of science, and the impact on healthcare. Ed?
So while they're finding my talk, I was struck as I listened to the rich science in all the first three presentations this morning. And it reminded me of an old Monty Python sketch, which was, "And now for something completely different." There will be no pictures of cells. There will be acronyms. I'm going to talk today about the evolution of personalized medicine. And the best thing about doing this is the one thing you know when you're predicting the future is that you're almost guaranteed to be wrong. So with that caveat and with that freedom, let me talk a little bit about the evolution and the economics of personalized medicine, which is going to influence the evolution quite significantly, and then some of the implications going forward. I'm going to start first with the evolution, and the potential for personalized medicine is quite vast. There's an opportunity to influence care across the full spectrum of disease, from kind of predisposition at the beginning through therapy selection and all the way to monitoring of the effectiveness of treatment downstream. Today, we focus almost exclusively on therapy selection and treatment, and that's where you hear about most of the advances. The benefit and the opportunity of the future is to expand beyond the tip of that peak into earlier stage identification and downstream into monitoring. And most of you probably know this, but personalized medicine is in a sense a reality today. There's more than 100 drugs that are already approved that have a biomarker associated with them in their label. There's more than 35 biomarkers that are referenced amongst those 107. So already we're seeing the influence of this. But as you think about the future and where this is going, I step back and say there's a huge opportunity here to accelerate what's happened over the last 3 to 4 years. And there are 3 big reasons for that. And then there's a couple of what I'll call governors or limiters on that acceleration. The first is that our basic understanding of the biology has increased dramatically. We have so much better understanding of the heterogeneity of disease and the influence of different genes and biomarkers of relevance. And maybe even, well, at least equally important, our ability to sequence and identify biomarkers has expanded dramatically. And the cost of that new technology and diagnosis is coming down faster than Moore's Law, which is what's driven the computer industry over the last 40 years, and creates a huge opportunity going forward. And then thirdly, we're starting to see insurers and payers and regulators look at personalized medicine and targeted therapy as a meaningful opportunity and put new regulations in place and create opportunities for payment for these types of personalized or companion diagnostic therapies that will help going forward. I was talking outside to someone who mentioned that they actually make the decisions on which tests to actually do based on reimbursement and the benefit of them, and that it's it's a system where everybody comes and says, here, I want to do this test. And it's not clear what the benefit is sometimes, and it's often not reimbursed. And so these steps by the payers and regulators are going to be central and critical to actually moving the personalized medicine world forward. There are a few barriers. The science has to continue to advance, as you would expect. We need to get better alignment among the stakeholders, and that means payers, there has to be demonstration of benefit that providers recognize. There has to be a payment system that can actually reimburse for the use of these tests and the alteration of therapies. And those things are not always in sync, and I'll talk about that a bit more in a moment. And then thirdly, there's a set of what I called operational challenges, which are basically we are generating massive amounts of data. Our ability to understand that data and then actually communicate it to physicians and other caregivers so that they can use it in the care of their patients is a tremendous challenge. And so better organizing and interpreting that data, creating communication or education devices to help support physicians and decision support tools is going to be a critical development for moving personalized medicine forward in the next 5 years. So let me just talk about some of these things that make me excited about personalized medicine. One is our understanding of the heterogeneity of the disease. And what you can see on the slide here is that we have come to a very good understanding of the number of genes that can be affected in different cancer types. But as you move across the slide, the experts think that of those 50 to 100, depending on the tumor type, there's probably 5 to 10 that are truly driver mutations. And then if you think about, well, what do we have to combat that in our treatment regimens today? We have, in some cases, one, or lung cancer, 2 drugs that actually target those mutations. But the good news is there's 10 to 20 in every tumor type that are specifically focused on those mutations going forward. And we will see those come into the marketplace over the next 5 years. And if you think about combination therapy, then just combinations against different mutations will expand the treatment options 100 to 1,000-fold in some of these tumors. The second thing is that the new diagnostic platforms and the reduction in cost and sequencing and other modes of data generation are dropping dramatically. And we did a panel of a number of experts in personalized medicine about 6 months ago, where we asked them how they thought next generation sequencing, as an example, would be used in the treatment of cancer patients going forward. And what you can see here is that for most of the major tumor types, lung, breast, colorectal, they think more than 50% of tumors by 2018 will actually be sequenced. And that will be used to help define what the therapy is going forward. So that will lead to a dramatic increase in our understanding and information about the disease and our targeting of therapy. But there's also an economic reason why they think this is going to happen. And that's that as the cost of sequencing goes down, our ability to do multivariate testing or testing of multiple markers simultaneously becomes much more efficient and effective. And so if you look at the left side of the slide, you can see some of the markers that are often tested for in lung cancer. And each of these tests costs somewhere between $500 and $1,000. And all total, it can cost up to $3,000. Today, sequencing can do that for about the same cost. But if you go forward 5 years, and you'll see, we're assuming, and we probably underestimate the degree that reimbursement will go down, but those single tests will actually cost less. But sequencing and doing all of them simultaneously will actually be cheaper than cherry picking, in a sense, the individual tests. I mentioned before there are a few challenges, and I'm going to talk a bit more about the operational challenges later. But one of the big challenges here is how do we make the most of the data that's being generated and that can be used to really accelerate personalized medicine. And the big challenge here is how do we begin to combine sets of data? We don't do that very effectively today. But genomic data and electronic medical records, or EMRs on the slide, are the ability to combine that so that we have genetic information linked to the longitudinal patient records and how people respond is going to be critical to unlocking and really accelerating our information going forward. And one of the reasons patient registries is so high is because we think in the future, at least the pharmaceutical industry, when they invest in things like registries, are going to demand or force both genomic and clinical information to come together. It's limited by the number of patients they have, but that will be one of those sets of data that's critical. So if you take all of this together, what does that mean for the evolution of personalized medicine testing? Well, today we're focused mostly on therapy selection in oncology and a few other select therapeutic areas, infectious disease being a prime example. And most of the emphasis, both in the press and also in terms of dollars, is on the pharmaceutical industry and companion diagnostics. As I look forward over the next 5 years, I think that a few things are going to happen. It's really an evolution, and hopefully it will be an accelerated evolution. But there will be dozens of new genetic markers that are developed that will help stratify your patient populations. We will see the multivariate or multiple marker testing assays come online, and that 10% to 20% of all drugs will actually have a companion diagnostic associated with them. That may not seem like much. In oncology, it will be far more than that. But if you think across the spectrum of where we're headed, there are many therapeutic areas where this is in its infancy. And then if I look forward another beyond 5 years, I think the majority of therapies will actually have companion diagnostics, and genomic sequencing will become the standard for all patients. And very importantly, as I mentioned before, patient-level decision support will come into play in the clinics and in the hospitals for the care of patients. So one thing I just mentioned I want to highlight is when we convened our expert panel, we wanted to look at across the spectrum of therapeutic area types, what's next, right? Oncology is obviously the leader in this space and provides a unique opportunity and to tailor therapies. And as you look forward, everything else is lagging behind, which is why I said in the next 5 years, we won't be there where a majority of drugs are actually personalized. But you can see that prenatal testing, transplant, and immune-related diseases are on the cusp. And CNS and CV are coming. So I'm going to shift to the second sort of main theme here and talk a bit about the economics of personalized medicine. And the first point here is we all believe that this has the potential to help everyone in the healthcare system. Patients first and foremost, but as you look at the economics from a system perspective, there's a real opportunity to reduce the cost of care and to improve the quality of care simultaneously through personalized medicine. And that's why the payer or insurance industry stands to have the most benefit. And if you just focus on reduction in treatment of non-productive treatment, meaning drugs that don't work for patients but they get anyway, and reduction in adverse events, there's somewhere between $70 and $100 billion in opportunity to save. Providers there's obviously diagnostic testing revenue, but providers, I think, stand to benefit as we look forward because we're moving more and more into a world where improved patient outcomes and pay for performance is central to how we think about providers and reimbursement. And personalized medicine will benefit that. Diagnostic companies and data players, just by virtue of what we're using more and more of, will have significant benefits. The one industry group that where it's more questionable how much they will benefit from the personalized medicine world, maybe somewhat counterintuitively, is the pharmaceutical industry. And I say that because the industry has no choice but to play just to be competitive. But if you look at what the potential for return on these types of therapies are for the pharmaceutical industry relative to the historic way that they have made money in their blockbusters, it's not clear that this will actually lead to benefit. And I'll talk a little bit about that going forward. So from a payer perspective, just a few slides that sort of tee up the benefit here. This is some data in some major disease areas that show sort of the overall patient size, typical drug cost, and the percent of people that don't actually respond to the therapy that they're provided. And you can see when you have 40 to 75% of people that aren't responding to the therapy they're provided, then there's a huge opportunity to target and better improve our selection of which patients get which therapy. And if you look at it from an adverse event perspective, this is some work we actually did with an academic medical center that was collecting germline sequencing and identifying adverse events for common drugs, things like statins or Plavix. And they were able to identify markers for significant adverse events in these circumstances and actually link that information proactively into their electronic medical records. And so in that case, they could decide not to start someone on statin because of a risk of myopathy, or decide whether or not to start Plavix in certain situations. And the benefit just simply across 3 drug categories was more than $2 billion if you roll that out to a system-wide perspective. So the potential is huge if we can overcome our, some of our data and decision support challenges. Now, diagnostic players, I sort of glossed over them at the beginning, but diagnostic players obviously are the producers of these tests and will make money off of them. The question is, how will they really be reimbursed going forward, and how will they be sort of considered in terms of capture of the value that's generated from this? This is a somewhat complicated slide, but if you bear with me for a moment. On the left, we have a list of diagnostics. So HER2 for breast cancer, BCR-ABL, and leukemia. And as you walk across, there are drugs that are targeted today based on those specific diagnostics. So Herceptin for HER2. The cost of therapy today for Herceptin is about $40,000 per year. 75 to 80% of patients are not indicated for Herceptin. So doing the test and deciding not to use it saves $30,000 on average per sort of test that's performed. And the test is about $100 today. So there's a 300-fold benefit in terms of the cost of the test to the tailoring of the therapy. As you move into other areas, though, which is sort of what I have in the next 3 rows, in other tests like for warfarin or Gleevec, that benefit or savings multiple is quite a bit different. It's much lower. The diagnostic company, in fact, consumes much more of the potential savings. And the real question here is what happens as we move downstream into other companion diagnostic areas, for example, other areas of oncology or rheumatoid arthritis or osteoporosis. And you can see that the test value, in other words, how it benefits the system, ranges quite dramatically from only $500 for an osteoporosis type agent or $300 for diabetes up to $15,000 to $20,000 for oncology. So our ability to figure out how diagnostic players can actually charge and who will reimburse at a rate that will allow them to continue to make these tests and actually thrive in this environment is important. Now, I mentioned that the jury's out on how much this helps the pharmaceutical industry in this transition to more personalized care. And we've done work looking in one large oncology player at their return on investment for all of their programs that are in their pipeline today. And I've bucketed them into sort of 4 broad groups. There's broad therapies, meaning they're available and applicable to multiple indications and types of people. But it's incremental in terms of benefit. It's not much of an advance in terms of the science and the clinical benefit. There are more transformative agents like that. And then there's personalized medicines, which are the 2 lower rows, where you have smaller niche therapies that are very targeted. And what we did was we looked at sort of anticipated market shares, probability of success, which is what the PTS is, and development cost, and calculated rates of return. And the mantra within the organization going in was, well, of course, personalized medicine is better. But as you can see on the slide, that's not so clear. The broad-based therapies generate a good return on investment. So do the personalized medicine. But even though, if you look at the 3rd row, even though the personalized niche therapy has much higher peak share, market share, much higher probability of success, and a lower variable cost, its return is fairly modest. And that's driven mostly by the size of the population that it's treating. So this is what drives a lot of the discussion around pricing and whether or not in the go-forward world, more narrow indications will continue to be priced higher than broad therapies. So finally, I want to talk briefly about the implications for business models and capability requirements. As I mentioned right at the beginning, I really believe that for personalized medicine to fulfill its promise, we need to expand beyond the emphasis on the pharmaceutical industry alone to move this forward. The reason is the industry is really focused justifiably on their proprietary therapies and how to best target those therapies to the appropriate patient populations. Well, that leaves a whole swath of areas that they are not emphasizing or investing in. So how you think about predisposition or diagnosis or prognosis. Therapies that are on market or generic today that may have significant side effects or benefits that they aren't being applied for. And so to get to those areas of opportunity, we really need to figure out a way to create a strong alignment between the insurers or the payment, the government, providers, and the diagnostic community as well. And there's a few business models that are evolving that will support this in different ways. And the first 2 are really focused around the pharmaceutical industry or drug therapy. And fee-for-service for the drug and diagnostic is the way we operate today in the United States. There's the opportunity to expand sort of appropriate utilization of the diagnostics by combining the drug and diagnostic pricing. So taking out that whole concern about whether the diagnostic companies can justifiably produce the test itself. And there are a number of industry players that are investigating that because the value of the drug and the therapy itself so far exceeds the cost of the test that it's well worth seeing if there are ways to change that paradigm from everything being separate to bundling together. There's also a lot of experimentation that I think could be quite helpful to the advance of personalized medicine in terms of payment revision. And that's in the area of episode or disease-based reimbursement. So moving from paying for every individual thing a physician does to paying for the treatment of a disease. There are many sort of pilots going on out in the United States today. And this, if it moves forward and expands, creates a real opportunity for focusing on really targeting the right patient to get the right therapy or to avoid the wrong therapy. And therefore, much more of a focus on advanced testing and planning in the treatment paradigm. And then population management or capitated care, where institutions get paid for the whole, for a whole population on a standard rate. So it doesn't matter whether they become ill or not ill; they get the same payment. This is an area, if the populations don't move around, where you can see lots of opportunity to do things to proactively identify and anticipate individual patient needs or individual member needs, and therefore test earlier and test before people are sick, so that when they do become ill, you can actually make the right decisions. And what's interesting here is there are a few institutions, mostly academic centers, that are now proactively banking blood and sequencing patients as they come in, and then linking it into their electronic medical records so that it proactively supports decisions that they're going to make downstream. Now, most of the reason for why they're doing that is scientific interest and the value of the potential value of the data to others, but they are actually moving it into the patient care paradigm that they're using. And then lastly, consumer payment, which I personally don't believe, at least in the States, will be a major driver here. But there are models such as 23andMe and Vita that actually charge you as an individual to go have yourself sequenced and then provide you with information or updates based on new information that comes out. So what is it going to take for us to be successful in this future world? Just from a pharma industry perspective, I just wanted to focus on a few things that they are trying to build to help sort of improve their personalized medicine paradigm. And the focus is, from research all the way through to commercial. In research, it's all about building up their biomarker capabilities, their tissue and sample collection and storage, and a ton on data infrastructure and analysis. From a development perspective, it's how do you change the paradigm and work with the regulatory agencies to be more effective and efficient and successful in filing. And then from business development and partnering perspective, you see you can see the press releases every day. There's partnerships for data. There's partnerships with health systems and academic centers. There's diagnostic company partnerships, all trying to create an ecosystem that helps support their new therapy introductions. And then finally, from a commercial perspective, the biggest thing here is thinking about how to drive, once you have companion diagnostics, how do you drive the education into the caregiving community so that they understand when and how to use it? So I'm going to stop here. I just want to make a couple points here on the summary. One is I think personalized medicine holds great promise. I think that really unlocking or accelerating this opportunity, though, it requires a couple of key things. One is making sure that we can get the incentives aligned in our complicated payment and provision system. The second is accelerating the convergence of the data and the interpretation and analysis of it. And then third is once all this information actually translates into specific clinical improvements or opportunities, creating a world that can provide decision support to physicians who would be overwhelmed by the amount of information and data that's going to be generated. Sure.
Yes.
I have talked to some of my physicians about their software for EMR, and they have told me that from one company to another, or from their own EMR system to a hospital, they're not communicating. Is IEEE or WE or anybody like that that's standardizing things across platforms and software? Are they working on this so that if I travel to California and I get sick,
Yeah.
can my electronic medical record go through the internet and to that hospital?
Sure. So the question is, today, the good news is we have, compared to 5 to 10 years ago with ARRA, we have many more electronic medical records than we did before. The bad news is they don't communicate. And the question is anybody working on that problem? And the simple answer is yes. There's lots of activity and investment in trying to figure out how to enable that communication. It comes in very different ways. You have everything from Epic, which is a large software player for enterprise systems that is trying to link up, already has linked up its hospital to its own ambulatory clinic capabilities. Now, they take a very proprietary approach, so some of the software standards that you were describing is not the path they're probably naturally inclined to do. Two groups that are banding together to, in fact, try to create a set of standards. And there is also a lot of activity in health information exchanges, so software that sits on top of the variety of systems and data, and then allows you to communicate and access that wherever you are. And those are places like McKinsey or Relay Health that do that. So I'm not. There's a lot of work to be done. Let me just put it that way. But everybody sees an opportunity there.
Sorry. Please, go ahead.
My question is, as we, particularly in oncology, we put a lot of our diseases into the chronic diseases, how does the reimbursement and the cost modeling and having to test for resistance and for defense-like therapies work in this reimbursement and cost model?
Well, you mean today's model or in the future, or both?
We're rapidly getting to this.
Yeah. So the question is, as we move to third, fourth, and fifth line therapies that are going to be driven by hopefully by testing to determine what might be effective, how are we going to be reimbursed effectively for that? Well, today, I will answer that. Today, it's going to have to be on at least the owners of the therapy, presumably innovative therapy, are going to have to convince the payers of the value of reimbursement for that specifically. If you're talking about generic therapy or the diagnostic tests themselves, then right now it's going to actually literally be not a case-by-case, meaning a patient-by-patient basis, but a diagnostic test by diagnostic test basis. I think what I was talking about before, which is using more episode-based care reimbursement or even sort of capitated care. In that case, it's critical to include in the calculation of what's the cost of therapy, all of those future lines of therapy. So that's the complexity of it, right? Because you can do that today, and then 2 years from now, the paradigm may be different. But that's what actuaries are supposed to be good at.
We'll give Dr. Yateman the last question.
Yeah.
Dr. Pleasure, Pelis, the honor last week in one of these buses for life sciences, tour machines.
Yep.
Sequence. And you plug in your DNA, you walk away, and 8 hours later you get a sequence back. The question is, recommend that every hospital, every pathology, buy these things and start doing sequences, or is it really going to be ultimately assimilated in larger labs like the last thing Lab4, and you could waste your time buying these desktop machines and doing it in-house? Lessons of research.
Well,
we try to. So Dr. Yateman's question was, for those that you couldn't hear, was, is it probably profitable right now for hospitals and medical services to buy some of the latest gadgetry that's been put on desktops, or should they wait until some of the larger companies push through the process of really using those procedures and being able to bill for them?
So I think that if you're going to do large-scale sequencing, or moderate to large-scale sequencing, the future is going to be in large centers, right? So an Invita, which is a startup company that's going to be sequencing hundreds of thousands of samples in a year, whole genome sequencing. I don't think you can compete with the cost. It's just too expensive for you to do it here. Now, if you're doing it for research purposes, as you mentioned, that's completely different. But I think 5 years from now, we're going to have much lower cost sequencing centers, and it's going to be far cheaper for you to outsource than it. And by the way, the quality and the standard of what you're doing is going to be higher if you do that.
Okay, thank you very much. Well, you know, up until now, I was going to give the Endurance Award for this meeting to our speakers that were yesterday at the BMW company trying to catch up with me, but were eating my dust as I raced away from them. But in fact, they don't get the award. I'm going to have to give that to Julie Robinson. Julie has been traveling to get here. It's actually, I think that the last 150 miles she had to walk last night at 2 or 3 in the morning in the rain. And I think that when she called Tim, he said, "No, I'm asleep. I'm not going to come pick you up." So, but anyway, so I do really appreciate that Julie got here because it was nip and tuck. I didn't know whether she was going to make it in time for her presentation on time or later in the afternoon. So I do give her the endurance medal and the Iron Woman award for this this particular meeting. Now, Julie is the program scientist for the International Space Station. As such, she has grown up through NASA and has worked on many various aspects, but she has had oversight in the transition of the Space Lab from the assembly period where there was just a few investigations going on to now it's more mature, full hundreds of investigations going on. She has received a Ph.D. in evolution, in ecology, and conservation biology, and to me that's really special because that's kind of where tumor growth really needs to be studied from those particular laws and aspects, and hopefully we'll see some of that mixed in. But she's had experience in just about every field of science that you can imagine, including chemistry and genetics, statistics, field biology, with remote sensing, and so well published. And so we're really delighted to have her. And one of the things I will point out, and I'm kind of disappointed, is that last night at a dinner, we actually had a piano in place, and I was hoping to be able to play as she sings a jazz and some classical, but unfortunately she didn't show up. So we'll just have to wait and hear that at a later time. Julie, thank you for being here.
It's a great pleasure to be with you today, and I hope you'll forgive the dark circles under the eyes, but I really didn't want to miss this because it's an outstanding group of people and an outstanding set of topics to really introduce to you the most amazing laboratory you never heard about. And so we began the day with a number of different science briefings that have given you a sense of the kinds of things that you can do if you remove gravity from the equation. It's a research opportunity that is unlike any other research opportunity that's available to scientists in the world today. And so I want to give you a little bit of background. We're getting closer to lunch. We're going to lighten it up just a little bit. And I want to give you a sense of what that laboratory is, why NASA built it, how it's available to you, and how you might actually start working that into your research plans. And it's a great transition then, because as I give you that overview, then we'll have CASIS after lunch able to talk to you about how they work with NASA to help users take advantage of the laboratory. So first, just a few facts, because if you've been busy in the lab, you may not have looked up in the sky and noticed there's something really bright going around that you can see every now and then. The International Space Station, whose assembly was completed about 1.5 years ago, is up there in orbit. at about 200 miles above the Earth. It's orbiting at about 17,500 miles per hour. It weighs almost 800,000 pounds. It's as wide as a football field, including the end zones. It is the most capable laboratory we've ever had in space. And unlike other laboratories in space, like the Space Shuttle, which we would have for 2 weeks every couple of years, we have it 24/7, 365 for the next decade. This is, I can show you the football field, and some of you will kind of get a feeling for that. Maybe if you're in the marching band, you have a better feeling for it than if you, or on the football team. But I think this picture actually helps to see how big this thing really is. And so this is a piece of the Space Station Truss. This is one of our 4 solar arrays. This is a little bit of one of the habitation modules. And this little inset here is called out. That's an astronaut in a spacesuit. So that gives you a sense of how big this thing is. If you could go there, you're going to be, it's like interacting with a shopping mall. It's huge. It's a big space. And of course, for those of you that like science fiction, here's another way to look at its size. This is how it compares to things that actually have never been built. So here's the space station here at about 107.4 meters. So we're not nearly as big as Battlestar Galactica. So what I want to talk to you about today is, first, I'm going to summarize why we do space research. You've heard little bits of that from our earlier speakers, and I'm going to try to put it in some graphical formats, some more visual formats for the visual thinkers here, so you can really digest what it means to take gravity out of the equation. And I'll talk a little bit about what's been done so far, what the most important results across all the disciplines are, and then finally, the real punchline is how can a researcher, including you, start using this laboratory. So first of all, you may think that because this was built by NASA, it's only available for NASA, and that nothing could be further from the truth. So in the NASA Authorization Act of 2005, while the ISS was still being built, there were 2 principles brought forward. There was a set of things that NASA would do with the space station. And those things are studying astronaut health and countermeasures to the health impacts that you heard Craig talk about today, so that we could send humans beyond Earth orbit, to Mars, to an asteroid, for long-duration future colonization of the solar system. Also testing research and technology developments for future space exploration so that we don't get halfway there and have our life support system break. That's running out of oxygen is what we call at NASA a bad day. Also to develop and validate our operational approaches for how we do long-duration space missions. NASA has been built on an intense mission control culture. And the further people get from space, the less people back here on Earth can be helpful or even, even make contributions at all to the mission. So there are huge operational changes we need to make in the way we do space exploration. And then finally, Congress said, yeah, microgravity life in physical sciences is important too. You can make some amazing discoveries, which I'll be talking about. So let's keep a little capacity there. But what you can see is that NASA's focus for what NASA research funding goes towards is very exploration mission driven. And the really wonderful thing about the Authorization Act is that it also designated the space station as a national laboratory. Well, what does that mean? What it means is that it's available for any other user outside of NASA who wants to do research there for those other missions that we have scientific research for all around the country. So other government agencies can sponsor research, provide funding for research, and they can fly that on the International Space Station. And NIH, for example, has had research opportunities on the ISS. Also, commercial entities, pharmaceutical companies, manufacturing, other industries can do research and development on the space station. And nonprofit organizations, including research institutes and academia, can directly access the laboratory without having to come to NASA for a blessing on funding. And so it's a really important shift in the way that the laboratory is used and the way that it's accessible to you as potential new users. It also specified we would meet our international commitments because, of course, this laboratory was built under a partnership of 16 nations, 5 different space agencies all around the world. So on the space station today, we are doing research in a number of different disciplines. And that's another unique aspect of the laboratory is the number of disciplines that do work there. And so here I just kind of broke them up in a nominal kind of a chart. And I divided it down that boundary I just talked to you about. The things that NASA funds for its exploration mission and the things that may be beneficial research back here on Earth that could be funded by other government agencies, private sector, and nonprofit organizations. And one of the big ones that's of interest to us here is biology and biotechnology. That's definitely one that we see interest in as much use on one side as we do on the other. Human research, which you heard Craig talk about, is very much structured, and you could tell that in his talk. It's very focused on our exploration goals. But that boundary is a porous boundary, thank goodness. And so there is opportunity for some research using human subjects over time. We have a process in place to evaluate that and look at that. Now, it has to be compatible with all the other experiments going on, so it's a little bit challenging, but it's certainly not out of the question. In the physical sciences, we see some industrial use, especially in materials, metallurgy, smart glasses, and so forth. Technology demonstration. Astrophysics is one. We haven't found anyone other than NASA that seems to be interested in funding a lot of work in astrophysics. But the earth sciences definitely have both commercial and nonprofit as well as NASA interest, and then, of course, education. So what you can see is the laboratory offers this extraordinary opportunity to a number of disciplines. So when Neal spoke to you earlier today, he talked about tissue genesis, and this chart is one that I borrowed from him a long time ago and have been recycling and representing ruthlessly over the years. Because what I want to give you is sort of the one-sentence version of why each of those disciplines would care about going into space. And I'll start with biology, because that's where we're most comfortable. And this cartoon I like because it just really illustrates you've got a cell, and it's Earth normal, and it goes into space, and it experiences a novel environment, and then all of the things that we would use to describe the metabolism, the functioning of the cell, its communication, its fluid distribution, its gene transduction, or signal transduction, its gene expression. And then if you bring it back to Earth, it goes back to Earth normal again. So it's an environmental response. In the same way that we have made astounding advances in biology from studying response to other extreme environments, such as the work done in the Yellowstone, looking at extremophiles led to the development of DNA sequencing, for example, and so, or RNA polymerases. And so in that same way, there's this novel environment, and although you can't predict a priori what you could learn from it, what you saw in Neal's work, in Neal's presentation this morning, is how that then can translate down the road into ways of looking at tissue genesis, ways of looking at stem cells, and so forth. We also have a set of plant researchers that are interested in doing work in space for a couple of reasons. One is that there are certain aspects of plants that are very, very gravity-centric. If you think about it from a seed's point of view, the most important decision that seed ever makes in its life is which way to send the shoot and which way to send the root. If that plant gets it wrong, it's all over for that seed. And so, in fact, plants have three different systems, three redundant systems for making sure they know which way to grow. And the only place that you can study those systems and actually separate them out in a solid experimental design is by going into space. Also, soil structure. You've heard us talk about fluid physics being so different, and I'll get to that in a minute. Those fluid physics drive the way that plants transport water, because plants transport water through surface tension forces, and they need to get it out of the soil, and that's very influenced by being in gravity. So plants in a microgravity environment are almost always drowning. Their roots feel like they're drowning. Another area where there has been a real interest in doing research in space is in the area of microbiology. And this is a cartoon to illustrate what has become apparent over the last few years of research into bacteria on the International Space Station. One is that there are three potential modes of response when bacteria fly into space. One is that some types of bacteria become more virulent. That's why they're colored red, because they're bad. Some other kinds of bacteria just multiply more rapidly. On a per unit basis, they're not any more virulent, but they're still more pathogenic because they're multiplying more rapidly. And then other types have no change. And this is an area of discovery. It was envisioned based on some ground-based research using bioreactors. It then went into space. And of course, what's important is you start learning what pathways are going on in that bacteria, how it's responding to the environment, what genes are turning on and off. That gives you insights into how the microbes cause disease. And I'll talk a little bit about more of that in a minute as well. Craig did a beautiful job of illustrating and talking about all the different stimuli from spaceflight and why that affects all the different physiological systems. And of course, not only in humans, but you can also study this in Drosophila, in C. elegans, in roundworms, and also in rodents. So NASA's focus, as you heard from Craig's talk, is really on figuring out how to transport astronauts safely so that, unlike Ed Lu here, who just landed after 6 months on the space station in Kazakhstan, he's not exactly functioning independently. And so someday when we go to Mars, we're going to land on Mars, there's not going to be any doctors sitting there waiting to check us out. So we've got to arrive on Mars fully ready to be independent, with our bones strong, our muscles strong. And that's really the foundation of all of the work that Craig talked about on the NASA Human Research Program side. But there are also dual uses. So there are also cases where what NASA needs for astronaut health are just as beneficial here on Earth, or perhaps even more beneficial. And so there's physiology and medical technology research in space. And I'll talk a little bit more about some of these, what we call spin-offs from NASA technologies as well. And so having talked about the biological, I want to just talk a little bit about the physical that underlies this. Because as much as we don't like it, in the end, biological organisms are completely subject to the laws of physics that underlie our Earth and our world and our molecules. And so the biggest difference, of course, when you go into a microgravity environment, an environment where gravity is canceled out by the free fall that you're doing as you're falling around the Earth to stay in orbit. It's not really gone. It's just canceled out by that free fall. And in so doing, we lose, as Craig mentioned, buoyancy-driven convection, sedimentation. And this little chart is just to remind you, if it's been a little while since you were thinking about physics and you're going, convection, yeah, I think I have a convection oven at home. This is just to kind of remind you that convection is that movement of molecules that you get when there are differences, when there are thermal differences. And then this is to show you how that translates into such dramatic changes in simple things. So this is a candle burning on Earth. You can think about this as your last birthday. This is that same candle burning in space. And so because you don't have thermal convection, you don't have buoyancy-driven convection going on there, all you have is, you know, this little bubble, and things aren't moving out the way that they do on the ground. And so that's just kind of just to give you a gut of how different that is. And so what I want to do is show you a video of what happens when you boil water. So here's, you can think of this as boiling water for spaghetti. And I want to show you a comparison of what happens when you boil water. To return to the meat. Of what happens when you boil water in space compared to on Earth. And here we go.
No input has been detected.
Okay, so on the left is regular boiling on Earth, and on the right, you see you get a flash boil, not the gradual rise to boiling. And then that flash boil, the bubble never rises to the top of the container. It stays in one place. And so we care about that on the NASA side because these two-phase systems, of course, are really important for everything from refrigeration to radiators, all of those things, the way we transfer fluids, so when we recycle urine, the way that the bubbles form in the urine, all of those things all are driven by fluid physics. So we care about it to build better space systems, but it also lets you study all kinds of physical processes that are usually hidden. So there are other kinds of convection, like Marangoni convection that's driven by surface tension forces. On Earth, the only way I know of to see that is to drink wine. So tonight, maybe you can try this out with your spouse. Take a really good glass of wine and you swirl the glass, and you see that sometimes a little bit of the wine will run up the glass. And those are called wine tears. That's an example of Marangoni convection. It's very difficult to study on Earth because gravity just swamps it out. But we can study those forces in space and really get fundamental equations for some of those. And that really opens up the ability to understand fluids. Well, what are organisms but really complex cellular blocks of fluids, right? We're mostly water. And so fluid physics is a huge part of the way that our bodies work. And so really the physics I just showed you here is completely connected to the way that cells and organisms respond in space and the way that you can use that to do research. And as I mentioned, of course, NASA wants to make sure all our technologies work, and so that comes into the picture. And then there are also the earth sciences and astrophysics. For example, the alpha magnetic spectrometer is sitting on the ISS. It's collected 25 billion observations of galactic cosmic rays. They just had their first publication announced last week in Physical Review Letters, which is the big cheese publication for particle physics, and have basically now proven without a shadow of a doubt there are too many positrons in the universe, which means that there's too much, something out there is going on that is creating antimatter. And that might be dark energy, which is pretty exciting, or it might be something nobody's thought of yet, which is also pretty exciting. Okay, so what has been done on the ISS? What are some of the most important results? First of all, just to date, there have been over 1,500 investigations done by researchers, many just like yourselves, on the International Space Station. Now, a lot of that began during assembly, and one MD who does research in space told me one time that during assembly, while we were building the space station, it was a little like trying to do surgery while they were still building the hospital. It was kind of difficult, but now that assembly's been complete for a year and a half, we really have the ability to meet researchers' needs on a pretty rapid basis, and so our pace has stepped up dramatically. Over 1,500 scientists have been involved, and there are over 700 scientific publications from work on the space station to date. Also, 68 countries have participated. If you remember, I said there were only a finite number of ISS partners, but of course science is quite international, and so there are great collaborations going on with the international community in the research on the space station. So now I want to shift to what kinds of benefits back here on Earth come from the research that we do on the space station. You know, so when you go to a novel laboratory like this, a place where scientists haven't really had the chance to test many, many things, you could argue, I've got a fifth grader, and she's doing science fair, and the first thing page 1 of the teacher's guide to doing a good science fair project says, you have to identify your variables, and you have to control them one by one by one, right? That's what we all learn. Gravity is the great uncontrolled variable, because if you think about it, the entire suite of scientific discovery from Aristotle all the way till now had gravity, and it wasn't controlled as a variable, it was just there. Now, a lot of times that doesn't matter, but we're still not sure all the times when it does matter. And so that's why this laboratory is so important at just getting through the basic processes of how physics works and how life works as well. So there are discoveries that come from this novel environment. There are the space exploration benefits that NASA's trying to make sure we've got all our ducks in a row for moving to the next destination. But what's really exciting are when you take those discoveries and you take those research results and you bring them back to Earth, and you bring them back in ways that protect human health, that make life better for people. And that can come from the research. It can also come from technology and other kinds of spin-offs that make life better here on Earth. So this is the crib sheet of where I'm going to go for the next segment of the conversation, because one time I was actually challenged by Charlie Bolden, the administrator of NASA, which is why I had to do it. I had resisted this for a long time. He said, well, give me your top 3 results. And I really didn't want to do that, because the results from the space station are like my children. It's like telling someone to pick your favorite child and then announce it for everyone. So instead of picking 3, I picked 12, which I thought was pretty good. I picked my top 3 favorite discoveries, my top 3 favorite things that contributed to the NASA exploration mission, my top 3 favorite results that might benefit Earth someday, and my top 3 favorite spin-offs that are benefiting people on Earth right now. And so I'm going to take you through a number of these examples in the next segment. So first, the area of discovery. I know we're talking about biology and personalized medicine and cancer research, but I have to share this with you because it was our first Nature paper from the International Space Station. This is an artist's rendition at the bottom of a black hole swallowing a star. So if you've been to a planetarium show, you may have seen this animated as well, where as a star gets close enough to the event horizon in a black hole, it gets sucked into that event horizon, and then you get a relativistic jet of X-rays that shoot out in both sides. And that's what creates basically a big X-ray signal in the solar system. And this is the before and after of just such an event. It was actually the first event ever observed by humankind where we could make measurements of the power of the energy. So these events have been observed a few times over human history, but if they're observed by eye with a telescope, you just see a new light. You don't, and then of course, if you're looking at X-rays, you can't see that with your eye at all, right? So here we've got the first time that this was actually directly observed. There were two instruments that observed it. This is the MAXI image from the International Space Station. NASA also has a satellite called SWIFT that was out there. It turned out MAXI saw it 2 hours earlier, so I was pretty tickled about that personally. And they put the data together, and this was our first Nature publication. Craig really talked already about the vision impacts and intracranial pressure discovery. And this is pretty extraordinary that after such a long period of human spaceflight that we had missed a fundamental and pretty dramatic impact on vision. And partly it was because we didn't have the subjects in long-duration flight until we had the International Space Station to detect the pattern. Partly it was because we were flying middle-aged astronauts, and everybody's expecting to start needing glasses at about that time, so we probably missed the pattern. And partly it was because we didn't have an ophthalmologist on task paying attention, right? Nobody thought about eyes as being, vision as being a significant problem. So we still don't understand the exact origin of this or the pathology behind it. One thing that's pretty interesting to me, there's a lot of focus on, of course, the intracranial pressure observation. And there are a number of different reasons that that might be occurring. And at NASA, we put that into what we call a fault tree, where we come up with all the possibilities and we try to start lopping off things that we can rule out. And our first investigation to really study this just began over the last 6 months. So it will be a couple of years before we start having some answers on this tree. But one thing that was quite compelling that came out early in the discovery, and it relates to individualized medicine, which is why I mention it here, is that if you look at the nutrition status of the astronauts, which is something we were doing in a completely separate study, the astronauts who had the vision loss were also more likely to be folate deficient. And some people that work with folate deficiency know that there's also a statistical correlation between folate deficiency and a certain form of the C1 pathway, basically a genetic difference or genetic polymorphism in humans. So we haven't even started looking at that in humans, and there are a number of reasons astronauts don't want you to do genetic tests on them and then say they can never fly again. So there's a little work to be done there to see if this becomes one of the first personalized medicine risks that NASA needs to take a look at for flying astronauts. But it's certainly an interesting correlation. So as I mentioned, one discovery is this pattern of microbial virulence. In one particular case, Cheryl Nickerson from Arizona State University found that salmonella became more virulent when flown in space. And the pathway that was turned on that led to that increase in virulence was a novel pathway for causing infection. So it was not realized that this set of ion signaling pathways would actually lead to a change in virulence in the microbe. And so now we've got a number of researchers that are looking at different kinds of microbes in space to see is this pattern conserved across different lineages of microbes. And that's also really a substantial discovery. So now I want to shift to some Earth benefits. And we've been working across our partnership to capture some of the major themes of Earth benefits. And the one I'm going to focus on the most today is obviously human health. But we've also worked in areas of Earth observation and disaster response, education. Now we're working on physical sciences and material sciences as well. So the first is what do you do with that discovery of microbial virulence? There are two competing teams right now trying to use that information to get further down the pathway towards vaccine development. One team has done additional space flights to see if they could use those results to screen for different variants that might be good candidate vaccines for salmonella to avoid foodborne illness. Also, they've looked to see if they might be able to use it for the screening of MRSA. And I think the jury's definitely still out on both of those attempts. At the same time, the original discoverer, her team at Arizona State, is partnering with a other members of that institution that have a vaccine for pneumococcal pneumonia that's in clinical trials, but that vaccine is not delivering the desired level of effectiveness, especially in elderly people. So many of you probably know we advise elderly people to get a pneumococcal vaccine, but they also respond the most poorly to that vaccine. So they're the people that need the protection, and the effectiveness is usually 50% or 60%. So it's an interesting way of looking at conjugate vaccines between salmonella and pneumococcal DNA to see if we could get a conjugated vaccine and improve its effectiveness. And the jury's still out on that one as well. Early in the space station, clear back in 2004, 2005, we did an experiment on, I would say, what you might call now kind of an old-fashioned approach to delivering cancer therapy treatments. At that time, back in the late 90s, early 2000s, looking at microencapsulation of chemotherapy drugs was kind of all the rage. It was before the Human Genome Project had its influence and people started looking at things a little differently. Scientists were interested in seeing if they could develop microcapsules that targeted to specific tissues, and there were some properties of those lipid layers that they thought might be possible to self-assemble in space without gravity better than you could do it on Earth. And so the teams did that. They were able to self-assemble microballoons in space. They tested those and found about 14 times more efficacy in targeting prostate tissue with those microcapsules in some animal studies. The problem was you couldn't get clinically relevant quantities of this waiting for space flights. So they sharpened their pencils. They spent about 5 years developing some equipment that could simulate enough of the microgravity environment to actually produce these kinds of microcapsules. That patent was issued about 1.5 years, almost 2 years ago now. And they're at the stage of fundraising for clinical trials. The trials have been approved at MD Anderson, but they haven't found a funding source yet. So it's another one of these things where the jury's still out, but it's an interesting and very different kind of an application than others that we've talked about so far. Macromolecular crystallization is another place where you can find the fusion of physics and biology coming together to give you access to new information. And this is an example from my Japanese colleagues. This is the best possible Earth-grown crystal. This is the best possible space-grown crystal of human prostaglandin D2 synthase inhibitor complex. And what was really important about this is a key part of the pathway in Duchenne's muscular dystrophy, which is a genetic form of muscular dystrophy affecting, I think, about 1 in 8,000 boys. It's quite debilitating form. The children are pretty much wheelchair bound by the time they're 9 years old. So it's dramatic. It's not as common as certain other forms of muscular dystrophy, but it is a pretty dramatic form in its impact on patients and on lives. And what the Japanese scientists found is that they got just a slightly better structure, really only about an improvement about 0.5 angstroms, so not a dramatically better structure, but they were able to identify how the inhibitor worked by seeing just a little bit more resolution on the shape of the proteins. And so they were able then to design a better inhibitor as a candidate treatment for Duchenne's muscular dystrophy. They've tested that. They've done preliminary tests in an animal model of Duchenne's muscular dystrophy, which in Japan is a beagle model, and had really dramatic results. And they're at the fundraising stage to see if they can take this further down the pipeline into more extensive animal trials, or perhaps begin the process for moving into human clinical trials. Okay, so I don't need to tell you this. I know that you struggle every day with how you take a research discovery and turn it into a patient outcome. But it's always important when I'm speaking with audiences, I don't want them to think I just promised them I would cure something, because there's so many things that it takes to do along the way. And so the same challenge that we have at NIH, the same challenge that cancer research institutes have, the NASA biomedical results from the space station are not immune to those. We have the same challenges in that there are so many discoveries that don't make it to the bedside, that don't make it to the patient, either because the market isn't strong enough and pharma doesn't decide to develop it, or because the side effects wind up being horrible, or because maybe once you leave the animal model, it just doesn't work at all in humans. And all of those things can affect the ability of these discoveries to make it to the patient. There are a few things, though, where we've worked on the International Space Station and they have made it into at least some level of distribution in the marketplace. And so I want to give you a couple examples of those. And generally, they are linked to things that are already in clinical trials. So this example comes from Amgen. They've flown several animal studies on the International Space Station over the years. And here you see mice from one of these studies. This is a study of an osteoprotegrin drug. And here you see the control animal. This is the animal that had the drug and flew in space. And this is the bones of the animal that didn't have the drug and flew in space. And so you don't have to actually do the bone density scan to just see the differences across those 3 x-rays. And so what Amgen did, they had already developed the drug through their normal pathways. But they were very interested in understanding its mechanism better as they moved through the FDA approval process. And so they used space as a way of challenging the mice and getting an understanding of the gene expression, what was going on underneath, to really understand the mechanism. And they did 3 flights. The first flight was on osteoprotegrin, and that now has come to market under the brand name of Prolia, democidab. And they also have a myostatin inhibitor and several others that they've tested on ISS that are in various stages of development process. Technologies from space also come back to make differences in human health on Earth. This is a picture of the robotic arm, the Canadarm on the International Space Station. This is a huge robotic arm that was used to assemble the space station, that we use to dock all our vehicles. So when a new vehicle comes up with all our medical research cargo on it, this arm actually grabs it out of space and then attaches it to the space station. So it's a pretty neat and important part of the way our vehicle works. But those technologies developed by MDA, those robotic technologies, have also now been miniaturized into something called the neuroarm. It can be used inside an MRI because of the things that they had to develop for radiation proofing and radiation sensitivity for use in space. And they allow neurosurgeons to do brain surgeries that they would otherwise have been unwilling to do because of the location of the tumor near a sensitive region of the brain. So you get the advantage for a surgeon, a neurosurgeon, who of course are the most stable hands of all the surgeons out there. And we've had a number of patients now who were considered previously inoperable. And this is a picture of one of them who's brought her story out to the public. There have been several hundred patients now that have been operated on using this neuroarm technology. This is a picture of a woman north of the Arctic Circle getting a prenatal ultrasound. So what on earth could that have to do with astronauts getting ultrasounds? And the reason is that NASA needed to have astronauts be able to do ultrasounds on each other as our primary medical diagnostic imaging. We don't have an X-ray machine, we don't have an MRI. All we have is an ultrasound. And we could not spare the time to send astronauts off to get 1.5 years of training as sonographers so they would be ready to do ultrasounds on each other. And so Henry Ford Health Systems developed an approach to doing remotely guided ultrasound where the astronauts needed about 2 hours of training. And then you have the trained sonographer on the ground, and you have a whole system worked out together so that the trained sonographer can guide the person who's got the probe in their hand. There's video feedback. There's also online training tools, and all of that together has allowed astronauts to collect really diagnostic quality images, ultrasound images on various parts of their body. We've actually discovered some amazing things about what happens when your organs are floating in space, which we didn't know before. But in addition to that, the spin-off value of that technology is extraordinary. So this woman living north of the Arctic Circle in Canada, this Inuit woman, is getting a prenatal ultrasound from a nurse practitioner who's also only had a few hours of ultrasound training. But back in a big city, connected via telemedicine, is a trained sonographer, and they're using this for prenatal screening so that if there's going to be a problem, she can be evacuated to a hospital before she goes into labor rather than waiting till she's in labor. It's a big crisis, a big medevac. You know, she's in a village that doesn't even have road access. And there's now a private foundation that's taking this technology and testing it in the developing and developed world. So Brazil is a big test case because rural areas have very little medical capability, but cities can have quite good medical treatment. It's also being tested in Africa, and it's been tested by the Detroit Red Wings and the U.S. Olympic team as well. Oh, and I should mention the American College of Surgeons has now adopted this as a training tool for their surgeons who also don't want to take a year and a half off of their regular residency pathway to become ultrasound experts. We also have technology spin-offs that come from things like our water recycling technology. And this picture shows you a packed bed reactor that's the technology that was developed for the space station because we wanted something to be compact and low power. It's been deployed in Pakistan after the earthquake back in 2008. And so these technologies come back to Earth, and they really can be used in disaster regions to help provide clean water, prevent cholera outbreaks, and they have really some extraordinary humanitarian benefits. So with that as kind of a suite, you can see how broad the space station is, how much it has to offer. And then the question is, how do you take what you know, the piece of science that you're most passionate about, and bring that to the International Space Station? So first of all, rest assured, you don't have to build space hardware in order to use the International Space Station. We have glove boxes, freezers and refrigerators, centrifuges, incubators, and culture systems. So we have all kinds of things on orbit that other researchers are using, just like the lab equipment you have in your lab. It's mostly not custom lab equipment. You buy it off the shelf. We've developed space versions of many of the kinds of hardware you might need in your laboratory. So how do you get funding? That's the next question. If the lab's there, it's built, it's got the things, hopefully, that you mostly need, how do you get the research there? And we call this our 5-phase template. And the first phase, of course, is getting sponsorship, getting the funding sources, finding the person who will say, yes, this belongs on the International Space Station, get it up there. Phase 2 is your strategic planning, making sure everybody's got everything together to support your research. Phase 3 is the tactical planning, training the crew, making sure they're ready to do your research. You can think of that as what you do when you bring a new grad student into the lab. Phase 4 is doing the research, and Phase 5 is analyzing the data. So I hope you notice there's something really familiar about this 5-phase template because it's the same template everybody uses for every bit of research they ever do. It's no different to take your research to the space station. And a lot of people just sort of have this feeling that, you know, it's NASA, it must be hard. And because we've got all of these great facilities now, that's the hard part, building the facility. But we have researchers that really don't know anything about NASA, don't even ever talk to NASA. They come in through what we call an implementation partner who knows how to do this in an incubator that will do what they need. And they just communicate about their science and hand the science over to this group to take up to the space station and do for them. Another important thing to know about sponsorship is that the American taxpayer, under the terms of ISS being a national laboratory, provides all the transportation. Any facility we've got, you can use. And the trained crew, the power, the data, all the things you need to be successful. All you have to do is raise the money to do or pay for what's basically your side of the research. And you can do that in 2 ways. You can raise that money by getting a NASA grant to do something NASA's interested in through research announcement processes. And those are always in a system called NSPIRES, so that's a good place to look at. If there are definitely biology opportunities there, opportunities in cell biology, opportunities in immunology is one area that's going to be open soon. That's also where you'll find Craig's Human Research Program announcements of opportunity every year. And there are opportunities both to do things on the space station as well as to try things on the ground first and see if those ideas are worth developing further, both through the Human Research Program and the National Space Biomedical Research Institute. But that's not the only way. You don't have to convince NASA that it's good for us. And that's huge. All you need to do is convince someone that it's good for them. So that can be a private institution, it can be a pharmaceutical company, and in that way you come up on the national lab side, and we've really done everything we can at NASA to try and make the cost of accessing things in space with reusing good facilities that we've already built about the same as the cost of doing things in a laboratory here on Earth. So for example, when we work with the National Institutes of Health and they select researchers, they select them out of the same pool of researchers that each institute is selecting from. The grants are at about the same size of a grant that you would get for NIH work in your own laboratory. And this has just some names, some points of contact. In your packet, you'll see there are web links and so forth. Everything I'm showing you here at this point is on nasa.gov. You can basically go to nasa.gov, click on the space station icon, and then you'll see a giant thing that says for researchers. That will lead you through all of these things that I've just talked about. And of course, the other way to do it, I mean, I always present both because I think the smartest researchers, right, you're out there, you're tapping the National Cancer Institute, but you're also talking to the American Cancer Society. You look at private funding, you look at public funding, you look at multiple government agencies. So it's good to know all the different ways to sell your idea up there. The planning and execution scares people because when you get ready to develop a grant, you start thinking, well, I don't know how to estimate the cost of that because I don't know what it takes to actually do it in a space laboratory. I would know how to cost that in my own laboratory. And the way that you work that is you find an implementation partner that's experienced in your area of research. And CASIS, who you'll be hearing from soon, has a wonderful index of all the implementation partners that they've worked with out there. And you can look at their expertise and you can find a company. And these companies are competing with each other. They're really relatively cost effective. And it's a great way to get that entree in and not really have to understand NASA or how to work with NASA. So then you work with them. You go to this implementation partner and you say, okay, here's what I'm doing in my lab. Here's why I think it might be interesting to do it without gravity. And then you tune in on the hardware that's already been built that you can use to test that. Then they work with you maybe to try some things in your lab with maybe a model system. And then you have, both CASIS and NASA have customer service systems to help you see if that idea is developed far enough that you can bring it forward, either for CASIS to help you find a good partnership. Maybe you have a partnership in place already and you've convinced them that this is worth trying. And so it's just so much easier than it used to be in the shuttle era and so much easier than you might think that it is. And so I'll stop leaving these links up here if you want to, just to see that they're actually pretty short links. And I'll mention, once again, the first link is the same place you get that I talked about. Go to nasa.gov, click on the space station, and click on for researchers. You'll get there. We have a Twitter at ISS Research, which is a way of following, if you like social media, it's a way of following what's going on every day, what the publications are as they come out. And we also have a research blog that really focuses on the experiences of the different people that we're working with, the experiences of the scientists, the experiences of the graduate students, discussion about things like omics analysis. There's a huge program coming down on the NASA side called Gene Lab that will be really focused on developing an open source omics database to compare what's all of the gene expression, all of the proteomics, the metabolomics in space to the databases that are on the ground. So that's going to become an extraordinary resource for all of you to start evaluating, looking at genes that maybe you're focused on in your lab. What are they like in your lab? How do those change in space? So there's a lot of really exciting things going on the space station that are things that you definitely need to take a look at and see if those will help you to jumpstart or make it an advance in your research. So thank you very much.
Well, so one of the messages I think I heard was, if you build it, they will come. So it's up to us now to be able to use this. Questions? We always learned, it seemed like a long time ago, microbiology, that whether you're in the northern hemisphere or the southern hemisphere, certain bacteria colonies would have certain swirls to them. Has that been tested in outer space? Do they have swirls there, or what goes on?
So the predominant forces of that type are just the little fractional bumps. So, we talk about it as microgravity, not zero gravity. If you notice, a lot of us NASA folks or people who'd been with NASA, we got that lingo going on, and people don't really know what that means. Well, the reason we say microgravity is because every time something bumps, right, you have a little G-force for that little bump. We call that G-jitter sometimes. And so you don't get sort of, the swirling toilet patterns on the space station because you don't have those kinds of, you don't have the Coriolis forces.
Are there toilets on the space station?
But there are toilets on the space station. They don't use water. They use
What
suction.
what about those big diapers that we've heard so much in the news that are good from driving from Houston to Florida with? Okay. Okay, so now the swirls, you do see them or you don't see them?
So you're not having Coriolis effects, so you don't see those swirls. Now, if you remember when I showed that plant, when I talked about plants, I had a chart and it had a circular-looking moss on it.
Yes.
So that moss was grown in the dark, so it didn't have either the blue light system or the red light system.
But it was green, looked like.
No, but so what plants have, and I know some of you guys probably aren't really focused on plant biology here, so you may not realize this. Plants have these 3 redundant systems. They have a gravity sensing system, a red light detecting system, and a blue light detecting system. So it's really, that plant is making sure it does not make a mistake. And if you take plants into space and you grow them in the dark, then they have no red light signal, no blue light signal, and no gravity signal. And that's what you get, that swirling growth in every direction, because the moss just doesn't know which way's up, so it tries everything.
Tim?
Yeah, I think people want to probably know where we're heading in the future. So when are we going to Mars? Why are we going there? And how are we getting there?
Okay, so the question is, when are we going to Mars, and how are we getting there?
Why?
And why? Okay, so first let me say that we have a lot of work to do before we're ready to go to Mars. And that's one of the reasons that the space station is guaranteed through 2020, and Congress has told us not to do anything to prevent operating it well beyond that. And actually, our estimates are that the vehicle should last well into the 2020s, maybe even as far as 2030. So we really have in front of us a decade to almost 2 decades of research access to the space station. And during that time frame, NASA is going to be perfecting a number of technologies that we need to go to the next destination. And that destination under the current administration is not set. It could be an asteroid. You may have heard in the news this week some discussion of actually lassoing an asteroid and then doing operations on that asteroid. There was a time under a previous administration where we really focused on possible going back to the moon and constructing a habitat. And there's some good reasons to do that, because we never really lived on the moon either. We only visited there, planted a flag. I think our longest mission was a day, really a day on the ground or 2 days on the ground. And by the way, our spacesuits had worn out because the dust is so caustic after 2 days. So we actually don't know how to live on another planetary body or a moon at all. But of course, the compelling destination, right, the one that really captures people's imaginations is going to Mars, because Mars is one that we could theoretically make habitable in not maybe in the next 10 years or 20 years, but certainly in the next couple of centuries. And so those who are far-reaching thinkers about exploration are really concerned about what happens when the next Chicxulub hits the Earth. So, if we had, at the Cretaceous-Tertiary boundary, a really large meteor struck the Earth on the Yucatan Peninsula, created the Chicxulub crater, and it's become a pretty strong consensus that that was a major factor contributing to the mass extinction of the dinosaurs, because Earth became a nuclear winter, and a lot of species went extinct. Mammals survived because they were small and could get around in the corners of the devastated ecosystems that were left over. Well, if a Chicxulub happened today, this would not be good for humankind. This would not be a situation that we could respond well to. Weeks and weeks of starvation. We're not small mammals that can get by on little bits of stuff anymore.
Building a bunker.
So you and the president.
So the far thinkers are really thinking about exploration as an important part of our economy and an important part of the survival of our species over the next 1,000 years. And Mars is definitely the next place to go from that perspective.
And conquest is always, in terms of the last frontiers, has just been something that I think humans have always wanted to do. Before you go there, Neal, you're next. Did you have a...
Just a quick question about, are there any plans in the future to increase the capability, the analytical capability for science on space station? The reason for the question is we may be able to get information much faster at ones and zeros rather than we discuss it.
Yeah, so we have a whole phase of analytical equipment development that's going on right now. And there are good scientific reasons for it, because when you bring organisms back down to Earth, you just subjected them to another transitional environment that isn't necessarily what you want to study. So being able to look at gene expression and things on orbit is a really important component of understanding what's going on in organisms. So there's a series of developments called Wet Lab that are phased in over the next couple of years. And it includes everything from PCR machines and genomics analysis, all kinds of things coming forward.
Okay, yes, one last question.
This is just, I'm curious about the creation of gravity. Is it feasible? And maybe it's just science fiction that I've heard or seen in a movie where you actually could create gravity in space by creating a centrifugal force. Is that something that would be feasible one day?
That is theoretically possible. The problem with it, and NASA's done a number of artificial gravity studies over the years, because 2001: A Space Odyssey was not, they weren't making that stuff up. Science fiction writers are smart. They look at what the scientists are thinking and they put that in. The problem is what I like to call the amusement park problem. So if you create a gravity vector by rotating, even in a really long arm centrifuge, the problem as a human being is if you turn your head off of that vector, it's not the same as being on Earth. So the effects of that vector on your vestibular system are not good. So even though it looks really cool in space, it's not like if you're rotating something, you would be just hanging out and behaving normally. You would never want to turn your head like that, because you would immediately get sick. It would basically be like having serious inner ear deficit all the time. And whether or not that would actually be an effective way for humans to travel in space is kind of questionable.
So they've tried spinning astronauts around?
Yeah, we actually do. We do what we call hyper-G studies, where we have astronauts, on different cycloergometers and different kinds of centrifuges, and try to study, how those vestibular effects, how those vestibular effects are working, and also whether or not that's even helping with things like bone loss and muscle loss. We've done some studies for a proposal that had come forward to put a small centrifuge on the space station that crew members would exercise on, to see if we could just rotate them in something kind of small and have them exercise on that. And that turned out to really not be feasible. And the problems of having, you couldn't get people on it long enough per day. And then there's another set of engineering problems that go with spinning your spacecraft. So, if you design for...
Please note, the meeting is no longer being recorded.
If you design... That's a
You
really...
can say what you want now.
If you design for microgravity, you know what your bubbles are going to do. You know they're not going to rise. If you design for gravity, you know your bubbles are going to rise, if you want to think about it that way. If you designed a system that was spinning all the time, you have to design it for that spinning, and then you have to design it to still work if it breaks and isn't spinning. So you actually have to design all your fluid systems to be able to work in either situation, and that's a pretty big engineering challenge as well. So NASA went a really long way down the artificial gravity pathway, and there's some neat reports on the internet. If you are having trouble sleeping at night sometime, you might want to look them up. There's some really neat reports on that trade space, and it's a pretty fascinating one from a science fiction perspective, definitely even. But what we found is that the engineering development costs, compared to what we've been we've been making these breakthroughs on, say, bone loss, where we kind of know what to do exercise-wise. And so it's looking like the countermeasure development approach that Craig talked to you about will get us ready to go to Mars, and we don't have to make all this extra engineering investment in a costly new set of technologies. Okay.
Well, thank you, and I'm really delighted, and I know we all are, that you did put in that effort to get here, because we would have missed this presentation, and I'm glad that we didn't have to. Thank you again.
Thank you.
Okay, so we're going to move on with the afternoon presentations, and I'm really excited to introduce Dwayne Ratliff. Now, Dwayne is the COO of CASIS, and he's the NASA liaisons. Now, the COO, as you know, has to take all the wonderful, beautiful ideas of the CEO and the director and actually make them happen.
The meeting is being recorded.
Oh, no, okay. Now I've got to start watching what I say. So that's what he does. Now, Dwayne went to school at Merrimack College and at Yale University. He's had a number of positions that he's held. He came to CASIS from his senior vice president of operations at Dynamac. And so he's experienced in being able to help investigators and CASIS get together to try to get the research that'll be going on the space lab. So I will tell you this, that Dwayne is going to be talking with Mike Roberts, and during his presentation he'll introduce Dr. Roberts. So, Dwayne.
Thank you, Dr. Pletcher. I actually have a really fantastic opportunity to bring us back in from lunch with a very special welcome message from outer space. So if you can kind of help me get this started. This was pre-recorded, but this is a welcome message from the International Space Station to the Gibbs.
Greetings from 240 miles above the Earth's surface aboard the International Space Station. I would like to welcome all physicians, scientists, and other attendees to the first ever Space, Cancer, and Personalized Medicine Conference. My name is Tom Marshburn, and I've been living and working inside of one of humankind's greatest technological achievements for over 4 months as an Expedition 34 and 35 crew member. I'm always thrilled when opportunities arise to promote the unique benefits and environment of the space station as a U.S. national laboratory designated for a wide range of scientific research. Nowhere else in the universe can one experience microgravity, extreme vacuum, and the cosmic radiation that are found on the ISS. The agenda for your conference today covers a wide range of interesting topics. You will hear from Dr. Tim Eatman, Dr. Julie Robinson, and others on topics such as stem cells, cancer biology, and personalized medicine, focusing on how your genome might help better tailor your future medical care. We hope that as you listen today, you'll find inspiration to design experiments that can be performed on the ISS in this one-of-a-kind environment to help make a fundamental difference in our understanding of biology and solve problems that cannot be solved on Earth. We wish you the best for your conference and for your future scientific endeavors as you let your minds wander creatively about what we might accomplish together in space. We will be thinking of you at the Gibbs Cancer Center the next time we pass overhead. As you gather next year, we will have made about 2,920 trips around the world. Enjoy the conference.
So I couldn't have said that better myself, actually. Oh, yeah, okay. Okay. So thank you for giving me the opportunity, Dr. Yateman, Dr. Pletcher, VCOM. I have a non-scientific presentation, which I will keep brief and concise because Julie has done a fantastic job of describing the International Space Station as a research laboratory that is quite diverse in its capabilities. And while we're focused here today on discussions on cellular research, cancer research, et cetera, I will point out very briefly that there are other scientific opportunities as well as technology development opportunities that are possible on the International Space Station. So I want to try to deliver my message in one of two ways. One, I'll do it through a video, which is kind of our 101 video that describes what CASIS is, and then following that I'll go into a little bit of detail about how we came about, how we're different in some aspects to NASA, and how we work very closely with NASA in order to accomplish our mission of making the discoveries on the International Space Station, National Laboratory, a benefit back to the ground.
What is CASIS? CASIS is the Center for the Advancement of Science in Space, and it manages the National Laboratory on the International Space Station. CASIS is launching a new era of space research to help reduce cost, increasing access and opportunity. CASIS is your gateway to innovation, breakthroughs, commercial R&D research, giving scientific, commercial, and educational industries equal access to space for the betterment of humankind. CASIS is appointed by Congress to identify the opportunities for the International Space Station, to take advantage of its unique environments to generate a return on investments, not only financially, but to improve life on Earth as well for the citizens of the United States. We do this by breaking down barriers, assisting in research, connecting, hardware, and funding. CASIS, bringing home the magic of space.
All right, well, maybe that last part was a little cheesy, but as I make that disclosure. So really, CASIS has a fairly simple mission, and that is, for the most part, to take advantage of the International Space Station as a national laboratory and utilize it to its greatest extent possible. But to do that by establishing the most promising research pathways that that unique laboratory can provide. And again, as I mentioned, it's a diverse opportunity. And probably most importantly is to make sure that everyone in this audience today and everyone within your scientific community are eligible, if you will, to become principal investigators for research that can be conducted on the national laboratory. So it's our role really to make this available to all other government agencies, academic institutions and interests, as well as private and commercial firms. So this concept of creating a national laboratory or a commercially viable laboratory in space is not really new. It's at least a decade old, and it probably is about as old of a concept as the station has been around with respect to being constructed. But some important milestones over the last 5 years have occurred to actually enable this opportunity today. Congress was a big driver. NASA, within its mission of exploration and its course of action, if you will, of constructing the station, realized that within its mission scope and its budget as established by Congress would not be able to fully capitalize the entire utility of the International Space Station. And so Congress, recognizing that, wanted to make sure that we could fully utilize what probably is one of mankind's biggest technological achievements. And so in 2010, with the NASA Authorization Act, that's what really extended the space station operations to 2020 at a minimum, and as Julie pointed out earlier today, hopefully beyond. But equally as important, directed NASA to identify a non-government entity to serve as a manager of the national laboratory, taking on some of the similar characteristics that we see with terrestrial-based national labs. And so midway 2011, CASIS was formed. And we've been working for a little bit under 2 years with NASA to serve as a sponsor for all non-NASA science and technology payloads that are destined for the ISS. The National Lab truly is a unique environment. We've heard from a lot of folks this morning describe some of those unique elements with respect to the physics of microgravity, or the lack thereof, if you will. And the ability for this novel environment, if you think fundamentally from evolutionary perspective of biology, this is an environment in which any organism that's been created in a 1G environment has never been exposed to. So it does create that opportunity for some novel exposures and observations to be created, which may help translate into application. There is a myriad of science that's already taken place, both fundamental and applied, over a number of years, thanks to NASA and its research programs. And so now we have access to that as kind of a starting point, if you will, to look at fundamental questions that have been asked, understand how some of those have been applied and how some of those may have not been applied, and try to identify what the gaps and opportunities may be in our own research questions. The biggest difference, if you will, and I don't want to make this sound as if it's negative, but the biggest difference with respect to our mission as the National Laboratory Manager and Julie and her colleagues' mission with respect to exploration and beyond is that we're really focusing on anything that we sponsor or fund or somewhere in between, that the benefit will actually return back to Earth. And that's not to say that there hasn't been tremendous return on investment with technology spinoffs and understanding across all kinds of different spectrums with respect to NASA's efforts. But this is one of the things that we're really dialed into. So CASIS as an entity, I should point out, as I mentioned, we're an NGO, but we're also a nonprofit. I really consider us a brokerage in a way. What we're here to do is to identify the unique aspects of that laboratory with respect to what type of science and technology development can be conducted, and then to identify interested parties who would actually like to use that facility for their research. And, I guess the third part, and probably the most important, is to identify novel sources, if you will, for acquiring the funding to make that possible. We have, again, as Julie mentioned earlier, a relationship with over 30 implementation partners. These are commercial firms who have a legacy history and knowledge of understanding how you take science objectives, integrate them into hardware and payloads, and successfully fly them to space. We work closely with NASA in our relationship with them to help understand what our on-orbit resource requirements are. They help us understand how we can identify contingency plans to ensure that our science objective mission is met. And NASA is our transportation logistics coordinator. So we work with the principal investigator as sort of their affiliate, their representative, if you will, to help communicate the requirements that are necessary in order for us to get the flight, the on-orbit operations, and the return successfully. So what our major value proposition really is, and we're piggybacking off of what NASA really is providing to everyone. Basically, it's a no-cost value proposition with respect to the ability to go to space, free rocket ride, if you will, all of the activities that would occur with respect to the use of crew interaction, the use of facilities or hardware that exist, power, data, cooling, communications, data downlink, everything that you can imagine that exists as a resource today is provided at no cost to our customers. And so that's a really pretty compelling sales point that we have. In addition to that, as the National Laboratory Manager, we have access to 50% of all of those resources that are available. So again, working closely with NASA, we help coordinate and communicate what our needs are so that we can actually expedite the time from concept on the ground through experiment and flight. And we work very closely with the implementation partners. So we have people who are experienced and they understand step A, step B, through step Z that you need to get to in order for a science objective to become a mission flight. And we really take advantage of that, as well as our relationship with NASA, to help expedite the process, knock down the hurdles that have typically been apparent in the past. And again, really what we're focused on is generating a return on investment back to the American taxpayer. And in addition to that, and equally as important, is we create opportunities to advance STEM education, advocacy of the space program, as well as outreach. And really, we have an opportunity that's rather unique when you think about how government agencies formally provide research opportunities. What's typically a grant process where there's a fairly finite set of rules or constraints wrapped around potential funding, we participate in a similar manner where we'll issue grants that have a designated endpoint. But at the same time, we also have the opportunity to engage in investigators who have an unsolicited proposal or a concept that's been generated from business development activities or networking. And while the generation of the idea is rather informal, it actually goes through our same evaluation process as a typical grant would, and I'll show you that in a second. First, I'll point out, though, that in the generation of how we prioritize what we believe is important with respect to using this laboratory, we've really done two major things. We've looked at all of the historical work that's been done and has been peer-reviewed and published. We have generated a clear understanding of the capabilities of the International Space Station from our relationship with NASA. But then we also assess the market. We look at the commercial terrestrial interests in the science capabilities, the technology development capabilities that exist and are available. And we understand what the biggest market need is. And from that, we develop our research portfolios. Those portfolios, again, translate into formal grants that we issue, but they also help us funnel our efforts and our focus when we conduct our business development opportunities, our fundraising opportunities, and our networking to go after very specific targets that would benefit most from this platform. And so this really just kind of represents those research portfolios and those objectives in the middle, and how through novel opportunities of outreach and developing partnerships, the solicited and unsolicited grant opportunities, as well as fundraising. There are foundations and other interests who have similar interests in tough-to-answer questions with respect to healthcare, for example, that may be funding sources to help support the research that we're trying to conduct. And then finally, on this outer ring, if you will, is the very fact that our customer base is pretty wide and consists of everything from academia to industry. At the end of the day, we're required to have a very fair and transparent evaluation process, really looking at three major elements. And one is the engineering aspect, and that is, can the science or the technology that's being proposed actually go to the International Space Station? So these are very fundamental sort of go, no-go questions that you ask, and it has to do with power requirements, mass, safety questions that need to be asked. And a lot of the times, it's not so much a matter of saying yes or no, but rather how can we kind of reformulate the package in order to make it viable for flight. Second to that, though, is a scientific review, and this is based on merit. Can we firmly evaluate a proposal and establish that within the portfolios that we see as important, there's actual merit from a scientific perspective, that it fits within that portfolio, and more importantly, needs the use of this unique laboratory in order to accomplish its objectives. Third, and this is probably novel, particularly to this group and to a lot of others, but there is a requirement for us to conduct an economic evaluation. And again, this is a formalized process, one that has a quantification applied to it, but really what we're asking is a question of, in our support, whether it's through simple sponsorship alone, which would require the use of resources on orbit that are paid for by the federal government, or across the entire spectrum of CASIS actually engaging not only in just the sponsorship, but the funding of a project, whether it's coming from its own coffers or partnerships that it's created through its networking opportunities. Can we perceive that there is an economic benefit at the end of the day that will be generated from the research that would be conducted? The first question I always get whenever I make that statement is, how do you put an economic value on fundamental or discovery type of science or research? And my argument is that while it may be difficult at that point, what we're ultimately looking at is the end point. Where might that discovery take us next? And so when we look at historically over time, the research that's been done through NASA, you can see that it's a number of years where some of these interesting questions that have been asked from a fundamental nature have actually translated into application that we appreciate today on the ground. So that's an economic evaluation that is conducted on our behalf. I mentioned the unsolicited proposals. And really, if you want to join our mission, as Julie pointed out earlier, we're involved in a number of ways. We actually share our social media opportunities. This is a way that you can contact us. But we actually also take place in forums that are probably a little unique to the traditional research forums. So we're really trying to understand the technological capabilities that ISS provides with respect to being a test, validation, and development platform. And so we look at innovative and entrepreneurial and startup organizations as well as potential customers. But with that, and based on the audience that we have today, I want to introduce and bring up Dr. Mike Roberts, who, there he is. Dr. Mike Roberts is one of our chief scientists within CASIS, and he is a flight veteran, very experienced in the translation of biology into spaceflight. And he's going to talk a little bit about some of the opportunities that exist up there. Thanks, Mike.
Seeing as we're in a very large lecture hall and we just returned from lunch and the blood's going elsewhere to parts of our body than the brain, I thought I'd start with a question. So today is April 12th. What happened in space history on April 12th? No. Could have been. That wasn't what I was thinking of. 52 years ago today, the first human orbited the Earth. So I thought, wow, I thought Kristen, when she organized this conference and picked this date, I thought, man, she's on it. She picked a very important date in space history. And it turned out it had more to do with the scheduling of this room, I think, than anything else. And 20 short years after Yuri Gagarin orbited the Earth, tonight is Yuri's night, the first space shuttle launch occurred from Cape Canaveral as well. So April 12th is an important date for us. I'll try not to ruin it right now. I'm going to take the baton from Dwayne and just dwell in a little bit, dig a little bit deeper on some of the topics that he touched on. Some of the slides I have are going to appear very familiar because you've had several speakers today that spoke far more eloquently in depth about the unique features of the space environment, but I'm going to try to bring some of those topics back to bear and how they can be important to your research and how you can get your research or your technology development up to the International Space Station and utilize it as you would your own lab, with the exception that, as has been pointed out, this laboratory is about 200 miles up and traveling at 17,500 miles an hour. As Dwayne mentioned, one of our primary goals is, now that Space Station is assembled and the National Lab has been created, is to utilize the unique capabilities of that station, of that laboratory, and the unique features of the space environment. And the realization has been made that NASA can't possibly fund all of the science that needs to be done or that could be done on the station, has benefit to that. So one way is to engage other governmental organizations, which NASA has done throughout the history of stations build-up. But they also want to reach out to investigators who may not have thought about utilizing the unique features of space as an environment in which they wanted to test their hypotheses. So in order to leverage additional funding to get more investigators, first-time space investigators up to station, CASIS has been charged with building new research pathways. So part of that means going out to solicit funding that can bring new investigators to station from academic institutions as well as other organizations. It also means that we want people to bring their ideas to CASIS thinking out of the box. So instead of relying upon a governmental body or CASIS, a non-governmental organization, to tell you, this is important science, I need somebody to write a grant to get funded to do this, you can bring your ideas to CASIS. And that was the unsolicited proposals path that Dwayne mentioned at the end of his presentation. Now, there have been several aspects of trying to do research in space that have discouraged investigators from fully utilizing the capabilities that we have for doing science in space. In many cases, the investigators felt that there wasn't clear scientific evidence that space research added value to the type of investigation or the type of questions they were interested in pursuing. More commonly, investigators felt that there was such a tremendous limitation of resource availability. The opportunities to fly were few and far between. The lead times to getting your science up to the platform and back were often lengthy. So for investigators who were coming from academic or medical institutions, if they wrote a grant, they couldn't tie any of their students or young faculty to a particular flight experiment because there was no guarantee they were going to be able to fly it in their lifetime at that institution. Furthermore, the way we do things in our lab is I'll speak for myself, frequently make mistakes. You learn from those mistakes, you go back and try it again, and you're able to iteratively improve your science over time. That aspect of doing research in the space environment is difficult because you have to wait for the next flight opportunity to improve the mistake you made the first time or the error you made. And often those time delays were too long and too critical to enable you to really get another flight opportunity to enable you to test your improvement to your process or the way you were posing your question. Another one that we continue to struggle with is communication. The astronauts are extremely highly motivated individuals, and they will make your experiment work. What they don't have is the same level of training that you have on your particular question or experiment. And your opportunities to communicate with them, to work their way through problems is very limited. So there's a premium that's put upon automating your experiment as much as you can so that you don't have to burden the crew with a lot of experimental manipulation that you would normally do in your environment. So you still have to keep that in mind when you're thinking about ways to do your science in a space environment. And last, limited funding, which we deal with in our ground labs, and it's no less true for the ISS National Lab as well. So this ties in with Julie's slide earlier about the 5-step pathway. So what CASIS is doing is taking that 5-step path and trying to define some efficiencies in there, ways that we can increase the level of funding to help identify sponsors for payloads, and to enable those of you who have ideas that can benefit Earth from exposure to the microgravity environment, ways to get those up to station and your data back in your hands and or your samples back in your hands as soon as possible. So part of that involves CASIS not only releasing formal requests for proposals where we define an area of research that we believe has significant value and can benefit from exposure to the microgravity environment. We also 24/7, 365 days a year, just like the station is operating, will accept proposals from investigators who have ideas that they think can benefit from exposure to station. You've heard the term implementation partners used today. Implementation partners are those entities, as Dwayne and Julie both mentioned, that enable your science to take place in the microgravity environment. So these are sometimes universities, sometimes companies, but they have a lot of experience in packaging your question into a particular piece of hardware that has been proven to work in the space environment. And they will work closely with you to format your question so that it can be addressed in the space environment. So no one that I know of has a habitat cage big enough to look at blue whale mating research in microgravity, so the operations guys are going to throw that one out of the door pretty fast. But if you have a question that involves cell cultivation, other things, there are a lot of different hardware platforms out there that can enable you to do stem cell science or that can enable you to do plant science investigations that most of the research community who hasn't flown or written proposals to NASA before may not be aware of. So CASIS can help point you in the direction of those implementation partners that have the best set of hardware or the best recent experience in flying the type of science that you wish to perform on the station. Going down to after the implementation partners, again, the goal here is to treat this as your own laboratory. So the idea is that you're not one and done. You will have the opportunity to fly multiple times if your science requires that and you can justify it. And the idea there is to make it more cost attractive so that, as Julie mentioned and Dwayne mentioned, you have the opportunity, you can afford to get your science up and back in a reasonable time and at a reasonable cost so that you can do vaccine development. NASA has already demonstrated that the ISS, in collaboration with commercial investigators, that it is a very viable platform for vaccine development, that you can do the type of science you'd like to do for preclinical trial studies within the constraints of launching and returning samples. So very quickly, you can tell this is a very popular picture with the candle. So the important thing to take home is that microgravity has very profound physical influences upon the biology that lives in that particular environment. So a lot of the changes that you're going to be looking at as an investigator may not necessarily be foremost in your mind caused by microgravity itself. There are a lot of secondary effects. I'm trained as a microbiologist formally, so I'm pretty confident that most microbes don't really care which way is up and which way is down, but they do care where their carbon's coming from. They do care where their oxygen's coming from. And all of those two-phase flow questions have a profound influence upon the cell's adaptation to that particular environment that it's in. So not only are you able to address questions that specifically focus on what is microgravity doing to my particular test system or environment, you also have the ability, as Julie talked about, of removing gravity as this kind of overwhelming force that all biological life has been exposed to since its evolution on Earth. So you have the capability of using the removal of this fundamental physical environment to determine new pathways, expose new gene expression patterns in your cells that can lead you to new discoveries. So part of the allure of the space environment is that we're putting our biology into a foreign environment to them, and we're just really looking to see what happens to them and how that influences their ability to adapt to that particular environment. For those of you who don't do biology, if you have a particular material that is of interest to you and you would like to expose it to the space environment, there are a wide array of opportunities that are available to you, and one of them is the ISS National Lab. In addition to the environment that's inside the crew quarters, the crew cabin on there, there is also a porch or a platform that's outside the station. So you now have the ability to expose materials or expose components of materials to the harsh environment of the low Earth orbit. The other advantage of being in low Earth orbit is that it's a wonderful platform. I think most of you have probably seen some of the videos and pictures of station simply as it goes through its orbits of Earth. You also have the capability with that orbit to capture about 90% of the Earth's surface that is populated, right? So for investigators who have need of looking at agricultural data or ocean data, ISS is a very viable platform for doing those types of Earth observations. One of the very early topics that came to the top of the list for ISS research was bone loss, because it happens to be of material concern to the human research program. In order to go farther into space and stay longer, we need to address the issues with bone loss. It also was of interest to investigators because you see an accelerated bone loss in the microgravity environment, and the capability of using animal model systems on space station was very attractive because you could look at them with an accelerated bone loss from over a very large point of their longevity in space. Muscle wasting is another area of research interest to both NASA's Human Research Program and has immediate Earth benefits because of the large number of genetic defects that are related to muscle loss. And again, in the space environment, you have an accelerated loss of muscle, and it offers an opportunity to test therapeutic targets in that environment and generate more significant data return for you in a short amount of time. Immune system effects. There we're dealing with the interaction, the interface between a large organism, humans, and their environment. We know from several experiments that microbes, again, even without a gravity sensor, are responding to the microgravity environment in which they're living. And that appears to have effects upon their ability to grow and divide in the environment that tend to reproduce faster. Biofilms tend to be more resistant to antibiotic insult. And the organisms also appear in some particular species of bacteria to be more virulent. And that's been tested both in vitro and in animal models as well. A very exciting area of research that will benefit greatly in the future years in the International Space Station National Lab is to look at stem cell biology. The focus here is to look at rates of stem cell differentiation. And this is where we hope to be able to see effects not only on developing new ways to maintain stem cell lines, but actually looking at omics types questions with the stem cell lines that we have. The ability to use induced pluripotent stem cells opens up a broad new array of ways to generate stem cells for personal medicine and personal therapy. One of the things that would be very interesting to do is look at the expression of the methylome of these iPS cells in the microgravity environment. Because we heard this morning that the epigenetic factors that are associated with that dedifferentiation is retarded somewhat in the iPS cells. And it would be interesting to see how the microgravity environment can actually influence that over time. Protein crystal growth has been a very active area of research for NASA and for the international partners on Space Station for a while. We've been limited a little bit in the ability to get crystals up and back. We finally now have the capability to get lots of crystals up and back. And I think you're going to see some very exciting findings coming out of the protein crystal growth experiments over the next couple of years. Plant biology, an area that's near and dear to my heart. One of the things that is of interest to us in fundamental biology is seeing how microbes interact with other organisms in the environment. The Human Research Program has focused some study on looking at the microbiome of the crew. We're also looking at the plant biome, how the microbes respond and interact with the plants inside of the crew environment. One of the things that another area of research and technology development for NASA required to sustain humans for long distance voyages from Earth are environmental control and life support systems. We need to do a better job of recycling air and water and possibly doing food production for long missions. We need to understand better how the microbes interact with the humans and the plants in that environment. So I mentioned the outdoor platform. So microgravity effects on fluid physics allow the study of very fundamental phenomena. And that interaction of physical studies with biological research is a topic of great interest to NASA now. And NASA is starting to look at ways to get the physicists, the fluid physicists, together with the biologists to identify new areas of research that didn't seem possible before. So we're actually going to try to look at the fundamental interfacial phenomena that occur between a cell interacting with the fluids in the microgravity environment that weren't possible before. I mentioned briefly the research opportunities in Earth and space observation. The International Space Station orbits the Earth every 90 minutes, so there's a lot of opportunity to look out the window and get very important Earth observations. And in that case, where you don't have to deal with sample return, it's also very easy to get your data back through data links. So how has CASIS moved to address some of these research areas? Last year, CASIS released a protein crystal growth RFP, and 5 proposals were awarded. And those investigators will be flying on SpaceX 3, which is currently slated to launch in November of this year. So in my previous research experience flying science on shuttle or station, from the time of grant release until award to actual flight, the average was about 3.5 years. We're now trying to do it in about a year. So from the time you're picked as a principal investigator, you should be able to get your science up on station in a year or less. That's the target. CASIS also recently awarded 2 material science proposals to go out on the platform. One of the exciting aspects of that particular proposal was we were working with a particular implementation partner who has adapted a very common form factor to their hardware design so that it's very easy for you to take their hardware into your lab and design your unique equipment that you need to complete your science in your particular laboratory environment. I'll leave that one for Paul. You good? Well, did I do that?
Oh, no.
It's not broadcasting slides anymore. I think it's just me. So if he doesn't accept, the last slide is on the unsolicited proposal link. So if you go to the front page of the CASIS website, iss-casis.org, there's a link on there for unsolicited proposals.
Sure what happened.
I'll just definitely get it. And I'll stop there. If there are any questions, I'd be glad to address them.
Maybe there's one question for. So it sounds to me like if we have an idea and we do have some things we would like to see in space, we can actually come to your group, maybe share that idea with you. You could then tell us about some of the problems that we need to overcome in terms of getting it from our laboratory to the space takeoff point to Absolutely. So we can see your group and your experts for that. Any other questions? Okay. Thank you. Oh, what? Well, probably myself and the president. No, those are questions, but I'm not sure. That's they'll put out an RFA to allow somebody.
We'd be glad to sell tickets, yeah. But beyond that, I really can't.
Those are that's a very interesting question, and let's see how it comes about. So I had a thing for and I think this goes right along with that. For many cases found that certain cases indicated that selected cases led to cases of confusion of the selected cases, which I think would be kind of appropriate. Okay. So now it gives me, I'm delighted to introduce Dr. Timothy Yateman, Director of the Gibbs Cancer Center. Most of you may or may not know that Tim is a Duke graduate and went to medical school at Emory, trained at the University of Florida, MD Anderson, is a well-accomplished surgeon and researcher in all the typical ways of proving that people have those expertises. But beyond that, Tim has worked for years in figuring out how to bring about personalized medicine. I can remember one of the first times we discussed this many years ago on a flight back from California. It was called Operation Whirlwind. I think he still has some T-shirts with that. So we're going to get a chance to hear a little bit about that. And Tim is going to present to us epithelial mesenchymal transitions, a new model for cancer biology. You may want to do this with just a marking pen on the blackboard.
I could do this with a marking pen. And I thought I'd start off by saying, this reminds me of looking from the space station down how small a world this is. You heard that phrase, a small world, and I'll tell you a short vignette. I met Mike Roberts for the first time in person last night, and we were just chatting, and I realized that he was actually a mentor to my son in the NASA science program at Kennedy Space Center, and that ultimately led to him applying for and getting into a Ph.D. program in mathematics. So it's a small story, but it tells you how important mentorship is. And what NASA does is education in the STEMS part of education. The second thing that I wanted to mention was that it may not be obvious to you, but the opening of the National Lab on Space just seemed to coordinate quite well with the opening of the Gibbs Research Lab. So that happened actually yesterday. And you're welcome to tour that later this afternoon. So I wanted to try to use this time to tie together this eclectic set of topics, which I picked, space, cancer, and personalized medicine. You wonder how they all tie together. Well, hopefully this talk will do some of that. So it's called the epithelial mesenchymal transition. We'll call it EMT for short. I don't have any significant disclosures. There's this theory, it was called the recapitulation theory, and another way, we heard it in medical school, ontogeny recapitulates phylogeny. And lots of examples of this sort of stuff where you have an antigen like the carcinoembryonic antigen is expressed in utero, and then it's re-expressed in a tumor later on in life. And the bottom line is cancer tends to mimic or piggyback on normal biology. So understanding normal biology and normal embryology is critical to really understand cancer. So EMT, as it turns out, is a normal cellular program where compact and organized, ordered epithelial cells stick together normally and make these nice single-layer membranes. All of a sudden, they lose those contacts. They become slippery, they become migratory, and they become mesenchymal. That's the critical nature of cancer. Cells leave their original partner and they travel, right? The thing that kills people with cancer is metastasis, and that's where tumor cell spreads from a primary location where it's sticking together nicely with its partners to separate and then land in a distant site and set up new camp. So EMT, this process of going from epithelial to mesenchymal, you can almost think of it as non-metastatic to metastatic, chemosensitive to chemoresistant. This process, they lose cell-cell adhesion, they lose their polarity, and they gain the ability to migrate through extracellular matrix. And these are the properties of a cancer cell. But this is normal EMT. So EMT is a reversible process where these cells, as you can see here, stick together, and they're apically oriented. And this would be a typical membrane. This could be in your bronchus. It could be in your colon mucosa, your stomach mucosa, any sort of epithelium, or your skin even. And then it goes to this organization where these cells can start traveling. And these have all these characteristics, multiple cell-cell contacts and normal polarity, going to being any direction, anywhere, and invade and move. So it turns out EMT is a normal process that's required for embryogenesis. And if we have medical students in the audience, it's one of the things that we didn't do so well in medical school. We skipped over very quickly was embryology. And it turns out that a lot of cancer biology comes from embryology. So EMT is required for embryogenesis, where cells must migrate from this neural crest throughout the embryo to give rise to different organs and structures. So much like we were talking about, Carol was talking about the blastocyst, and that was the earliest part of embryology. You can see here that she was sort of in this zone, and she was talking about taking these cells and making a stem cell population from that. But as you go a little further, these cells form what's called the neural crest right here. And this embryo is this shell, basically, that's seeded by these cells. So at this point in time, these cells start dispersing and traveling all over the embryo. So in order to disperse and separate from this, guess what they have to do? They have to separate from their primary mass. They have to change some molecular characteristics. They go through EMT. So another view of this is actually this, where you're seeing this neural crest and these cells are starting to disperse. And these are the molecules that are actually involved. Snail, incoherin, ecoherin, things like this. And what you'll see is these same genes that are involved in normal embryonic EMT are the same genes that are hijacked in cancer. So another interesting thing I've noticed is, again, embryology, is that, and I'm a colon surgeon, liver surgeon, so I spent a lot of time looking at the colon, and it has two blood supplies. You probably didn't know that, but one is from the superior mesenteric artery, and the other is from the inferior mesenteric artery. So this is the right side of the colon, the left side of the colon in the embryo. And when you go to the adult, you see the right side of the colon here supplied by the superior mesenteric artery, and the left side supplied by the inferior mesenteric artery. So the right side of the colon, left side of the colon come from two different parts of the embryo. And what's the significance of that? Well, the significance of it is that, in fact, colon cancers that arrive from this side are different from the ones that arrive from that side. They're genetically different. The molecules are different. They're not the same thing. And we're now learning that. And they have different behavior. So normal EMT is also a process required for wound healing. Again, when you heal a wound, cells must migrate into an open wound. You have a cut. You have a big defect. They've got to migrate into that wound and heal it. And so all sorts of cells migrate into a healing wound. But this is your typical wound, and you see fat here and so forth. But there's a lot of inflammatory tissue. If you watch this wound and just packed it with saline gauze over the course of 2-3 weeks, it would just sort of close up. What's happening is it's being infiltrated by all sorts of cells, and the wound healing process is occurring. In order for the cells to do that, they have to go through EMT. So here's another example of EMT. And this is what really happens on the molecular level, showing the infiltration of PMNs, macrophages, platelets, blood cells, ultimately fibrin. We talked about the stem cells and requiring some kind of sort of basement membrane and structure to go into. I think we heard about tissue engineering from Neal, how you had to have some sort of structure. And this is what happens in wound healing. It lays down this structure, this fibrin structure, and then you get a cellular matrix put on top. So this is, again, just to show you an EMT, what's really happening, where you normally have the cells all stuck together here nicely in this sort of area, and a wound has occurred, and now cells start releasing from this wound to get in here and grow and fill in the space. And the same molecules that I mentioned before are involved in this normal process. So you see ECAD here and there, beta-catenin, things like that. So you can't make this up. It's too coincidental, right? So you really do have to study embryology to understand this. So normal EMT is required for normal colon development. And this is fascinating too. So the colon, when you actually look inside, it has these things called crypts. There's these absorptive surfaces, and they look like this, up and down, these big holes. And basically, this is created this way. You see, you have a tremendous absorptive surface. And the purpose of the colon, for example, is to absorb a lot of water. So you have these tremendous absorptive surfaces to do that. Well, it turns out there's a lot of cells here. Each one of these is a cell. These are goblet cells filled with mucin. And what happens is, it turns out they're actually made down here, and then they start to differentiate, and then they ultimately die. So the life cycle of a colon crypt is about 4 days. So these cells start as stem cells down here, and they become proliferating cells, differentiating cells, and apoptotic cells. There's actually some great videos online you can find that show how this happens. But basically, again, the stem cell is here. It starts creating these other cells, and they progress up this crypt, ding, 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 until they ultimately die. And there's lots of molecules involved. One of the main pathways is called the Wnt pathway, and that is the pathway that, in fact, is responsible for the maturation and ultimately the death of these cells. So it's no surprise that the Wnt pathway is one of the primary targets in colon cancer, because if you think about it, colon cancer, you wouldn't want the cells to die. A colon cancer would continue to live on forever. And to do that, it hijacks the Wnt pathway. And so these cells start multiplying here. Instead of going up and differentiating and dying, they grow a tumor right here. And this is the genesis of your colon cancer. So EMT may also contribute to the development of cancer progression and metastasis. And not only initiation, which I just showed you, but also progression and metastasis. So those are really two different things. And again, cancer follows this embryologic model. So you start with epithelial cells that have these nice tight junctions, and then you go through this EMT process, and you start to lose those junctions, and ultimately get these mesenchymal cells, which are bad, because they look bad. They look like they can sort of start traveling and going somewhere and setting up camp. Now, it turns out that cells go through this process by changing these molecules and changing these molecules. And when you change these molecules, the expression of these, you get two different types of cells. And it turns out when you've got a cell that starts out, for instance, in the colon and gets into the bloodstream, it looks like this mesenchymal cell in the bloodstream, we think. We think those are probably circulating tumor cells. You might have heard of those. And they're probably very resistant to chemotherapy as we know it today. They probably don't divide much. They're probably just floating around, almost like the tuberculosis bug that can hang out in your lungs for years. These can probably hang out in a lymph node or in the blood for a while, avoiding the immune system. But then they seed a distant organ site, and guess what they do? They go back through a process of transformation to the epithelial cell again. That's how they reform a tumor in a distant site. And that's why, if you look under the microscope at a colon cancer, primary colon cancer, and take a piece of that, and then go to look in the liver, they look the same. It's because the primary tumor was recapitulated in the liver. And we think that recapitulation process involves stem cell biology. Stem cells allowing you to recapitulate the original tumor. So again, this is this picture of the crypt, and you're talking about the cell here that normally spreads out and derives these other cells. And this is the formation of a lesion. And we think what happens is these particular cells, because they're living a long time and not dividing too much, they can get multiple hits over years. So it takes probably 17 years to get a regular colon cancer developed, and probably 5 or 6 key mutations. And so you can't have that occurring here because these cells are dying and being shed. So the obvious place to target for mutations is probably here. And that's what's really happening. Then you get these tumors forming in the midcrypt, and they ultimately form your cancer. So again, this is another image of this whole thing showing you the epithelial mesenchymal transition and the mesenchymal to epithelial retransition back. So you've got a primary tumor, it turns mesenchymal, gets in the bloodstream, seeds a distant site, and then goes back through that progression back to the epithelial type. And so it makes a tumor that looks like that one when you're done. Same story here, just a different view. So abnormal EMT is a result of the concerted action of numerous genes, many of which are hijacked from normal EMT. So we spent a lot of time in our lab really looking at EMT and identifying the genes that are associated with EMT. And this is what's called a wordle. And basically the size of each word, each one of these is a name of an individual gene. And the size of the word gives you the idea of how important that gene is in the pathway or the process. So TGF-beta is probably one of the most important genes in EMT. And it turns out it's a gene that really causes slowing of cell growth. And so in terms of EMT, it turns out the gene that's mutated is the TGF-beta receptor. And so that gene can no longer slow growth. So this thing becomes basically a gene promoting EMT. Anyway, you see loss of adhesion, invasion, motility, metastasis, resistance to therapy, and tumor stem cell biology. Those are characteristics of the mesenchymal cell. And on the right-hand side, you see that those cells lose a gene called CDH1, which is ecoherin, and increase in these genes here, which are transcription factors that control a whole host of other genes right in here. So there's a whole pathway of genes that are controlled, going from epithelial to mesenchymal. And what happens is genes like TGF-beta starts regulating all these transcription factors that regulate a whole host of genes that cause this big transformation from this to this. So you don't go from here to here without changing a bunch of genes, the expression of genes. This is not mutation of genes, just expression of genes. So TGF-beta is critical in promoting EMT. And I told you how you could have a mutation in the TGF-beta receptor, and that would cause a problem. So it turns out that when you have a mutation in the receptor, it causes a disease in colon cancer called microsatellite instability. And it's also, this particular defect is the end product of a familial thing called Lynch syndrome, where you inherit colon cancer. So I wanted to sort of take you through briefly what we've done in our lab to support this sort of background and where we're going to go with this. So I spent about a decade studying gene expression analysis, primarily focused on colon cancer. And we call these molecular fingerprints. Basically, when we started this project in about 2000, we thought there were 100,000 genes. It turns out there's probably only 20,000 genes. But each one of those can be differentially expressed. But at any one time, it's probably only 5,000 genes that are differentially expressed, not all 20,000. Many of them are silent. So, you can boil cancer down to looking at 5,000 differentially expressed genes, and of course, a lot of mutations. So omics, and I know that NASA has a big omics project plan called Gene Lab. But omics is a study of not only DNA, but RNA, protein, and the metabolome. So we're talking about looking at, remember DNA makes RNA makes protein. You remember that from biology in high school. But bottom line is you can study each one of those individual things and get information out of it. So you can study the gene, the DNA, by looking at DNA sequencing. And that's what we're in today, in the midst of. The last 10 years, we were in the midst of looking at RNA, which is the transcriptome, which is what I'm going to talk about today. And the proteome is a little bit off still because the technology isn't quite as ripe. So to look at gene expression, we used a gene chip. It was called an Affymetrix gene chip. And it's a little chip like this. And believe it or not, on that chip, you can look at the entire expressed set of genes, 20,000 genes. And over the last 6 years, we did a project with Merck that built the world's largest tumor biorepository. We actually collected about 30,000 frozen tumors with hospitals very much like the Gibbs Cancer Center, and then profiled many of them on gene chips, 20,000 of them. And 2,000 were colorectal cancers. So we are actually sitting on the world's largest colorectal cancer gene expression database and now able to interrogate that. So the way this works is that little chip I showed you there has a silicone wafer on it, like a computer silicone wafer, and a number of DNA probes are annealed down to it, and those DNA probes will detect the expression of individual RNA genes, and so you can see the expression of individual gene based on how much it lights up on this little probe. And that's another image of how it works. You take RNA out of the cell, you label it, you throw it down on this gene chip, and you run a laser over it, and you get a nice image of the expression of each of the 20,000 genes. Now you can take that expression of thousands of genes, and I told you there are 20,000, but you notice there's only 5,000 here because there's only 5,000 roughly expressed in cancer. And you can express them across, in this case, 350 tumors, but we actually had 20,000 tumors, and we just did it for 350 here. But this is the expression of 350 tumors and 5,000 genes, and I think you could probably see two patterns, this one here and this one here. This is the reverse, the sort of red here and red there and blue there and blue there, the reverse image of each. What we did in this experiment with my colleagues at Merck was to try to identify what we took a whole group of colon cancer patients and asked the question, can the gene expression data tell us anything? So we really went to the mathematicians and statisticians and said, look at all this data. Can you tell us anything from it? Because we didn't want to go into it with some preconceived idea that there was something there. So they created this model they call right here. It's called the first principle component, and it separated these two groups, this one and this one. You can see the difference. And we didn't know what those two groups meant or what they were. So Merck had a series of 1,500 signatures, gene expression signatures in the bank, and they ran those signatures across against this pattern. And one popped out with an incredibly high correlation. If you know anything about p-values, this is p 9 times 10 to the minus 135. So remarkable relationship between Merck's EMT signature score and what we call the first principle component of the colon cancer data, suggesting that the two different populations that exist in colon cancer are epithelial and mesenchymal. And of course, they developed a signature with cell lines using CDH1 and vimentin. And that CDH1 keeps popping up because when I first showed you the neural crest picture, CDH1 was on that picture. It's one of those genes involved in EMT. And now I'm showing you involved in colon cancer in this EMT signature. So we created this signature for colon cancer, and it involved 149 genes that were upregulated and 160 that were downregulated. And many of them were associated with the process of EMT, like ZEB1 and things like that I pointed out to you, snail. And many of them are represented on this EMT diagram, starting with TGF-beta and activating some of these things we talked about, snail, slug, beta-catenin, and so forth, twist. So what we published in this paper with, in BMC Genomics was that EMT appeared to be the dominant program in human colon cancer. And that's, I think it's going to be reconfirmed in a paper this week in Nature Medicine, because we saw a paper at AACR that talked about EMT and colon cancer, and I don't think they could avoid our paper, not referencing it, but basically we took this EMT signature and related it to things like recurrence of colon cancer. And you might expect that if you had a tumor that was high in EMT, in other words, it's mesenchymal, I told you mesenchymal is bad. Mesenchymal means metastatic. Well, that correlated with tumors that were in fact recurring. It correlated with tumors that were higher stage. And it predicted poor prognosis. So these are patients with the mesenchymal phenotype, and these are with the epithelial. So you see a nice separation of stage in 3 independent data sets. So more recently, our data suggests a relationship between this microsatellite stability I talked to you about in EMT. And microsatellite stable tumors are tumors that are more epithelial and have more mutations and better prognosis. So I'll say that again. This was a big surprise to us and others that when you look at colon tumors, there's some that have almost no mutations at all. And there's some that have 1,000 mutations in them. Which one do you think would have the worst prognosis? You'd think the one with 1,000 mutations, right? Because there's so many things awry. As it turns out, it's just the opposite. The ones with thousands of mutations have a very good prognosis. They tend not to metastasize. They tend to be more epithelial, and they tend to stay put. And we think the answer may lie with immunity, because they produce so many mutations that the immune system can actually pick it up. Well, it's funny you should ask. It does, because on the right side of the colon is where you see all the MSI cases. On the left side, you see all the microsatellite stable cases. So I don't think it's any surprise. What's really happening, we think, is over here. There's probably a lot of methylation going on, methylation processes. And we now know methylation processes are part of the embryologic development cycle. So the MSI pathway is on the right side of the colon. These are often poor differentiated, mucinous, but have a better prognosis. It's really strange. On the left side, they have fewer mutations, more lethal, more aneuploid, and less immune infiltrate. So microsatellite stability dominates the right colon, and you can see the red dots here are these MSI cases, mostly on the right side, and are actually in the blue here. And the red are these methylated cases, which is another story we won't get into. The only other thing I want to mention to you is that there's another whole thing out there called microRNAs, and we're studying those in the lab now too. It turns out the body has lots of ways to regulate gene expression. If there's 20,000 genes, somebody's got to keep track of them. And so there's lots of ways to keep track of them, and one way is microRNAs. These are small pieces of RNA. We used to think they're junk, part of the junk genome, but in fact they're very important in regulating the expression of genes. And it turns out that each microRNA can regulate about 100 genes at a time. So it's a way for the body to turn on a whole program of genes at once, or turn off a whole program once, sort of master switch. And these microarrays generally silence genes by mRNA degradation. So we did an experiment where we had all of our tumors lined up by our EMT score, and then we ran a microRNA analysis of them at the same time. And we compared the two and found that certain microRNAs correlate with EMT. And it turns out that we found some novel microRNAs that correlated with EMT, as well as some standard ones. And in the lab, we've started experimenting with some of these novel microRNAs. And I'll give you an example of what EMT looks like. So you probably can see here, these cells look mesenchymal. They're spindly. They look like they're traveling and moving. But when you get over here, what do you see? You see them more shaping up and grouping, and not as much. So there's a clear change from here to here and here to here. These are the epithelial, these are mesenchymal. This is a mesenchymal epithelial transition, and it's brought about by treatment of those cells in the lab with MIR200. Now we know there's probably a lot of MIRs that will take you from EMT and MET and in these various steps of this process. So lots of regulators to keep track of. And to show you the power of one of these things, I showed you the change, the physical change. I'll show you the only Western blot today, but this is a Western blot showing you proteins. And basically what you're looking at here is where we took cells and we treated them with this MIR200, and we were able basically to induce this CDH1. So you see no expression here. All of a sudden, this thing, it turns on. CDH1 turns on because we went from a mesenchymal epithelial transition. And this is the sticky molecule that allows cells to stick together in the membrane, and it keeps them from metastasizing. So we've induced that, and that's a good thing to do, right? If you could actually revert cells to the epithelial phenotype, you might make them less metastatic. It turns out you can not only induce that, but you can do it on the surface. If you go up to our labs and see, we'll have a flow cytometer there, and we measure the cell surface expression of genes. And here you can see how this blue line is shifted to the right because more and more expression of that ecoherin occurs. And guess what? It's put actually on the surface of the cell, allowing it to stick to another cell. So it not only put more on the cell, but it put it in the right place. It could have put it in the cytoplasm somewhere, but it stuck it on the surface. And I'll just skip through this, but we basically have found other mirrors to support our model. So the summary model is we think now that you got this primary tumor sitting out there and that there's a cancer stem cell or two in it. There's got to be a cancer stem cell in it too somewhere because in order for that primary tumor to metastasize, there's got to be a cell that can get out through a process of EMT and stick in a distant organ site and recapitulate that primary tumor in the liver or the lungs or the brain. And so that's probably the process. So in summary, I think EMT is a normal process, as I said, used in embryogenesis, wound healing, colon development. It has an abnormal role in cancer development and progression, where basically stem cell development has been hijacked, and a number of these genes have been hijacked, and mutation has occurred, and you also have this process of EMT occurring that allows metastasis. So colon cancer, we think, has two principal classes: good, epithelial, and bad, mesenchymal. We now have gene expression profiles that can predict those. So somebody we heard earlier, personalized medicine signatures are out there. We actually have signatures now that can predict good and poor prognosis colon cancer better than staging. There's not a lot of market potential for them because we don't have a drug to go and act on it. To tell you you're going to do better or worse doesn't really help you unless your doctor can say, well, I've got this to treat you with now. It just gives you less hope or more hope. So gene expression signatures can be found to distinguish epithelial from mesenchymal tumors, and that's personalized medicine. The gene signature is linked to EMT genes, and microRNAs also control gene expression in EMT. So what's the future? The future is we're going to go from gene expression to sequencing, and we're going to start relating mutations to EMT. So we've started sequencing tumors that have high and low EMT scores, and we're relating mutations between the right and the left colon. We now know that colon tumors on the right look different than colon tumors on the left, and they have different sets and patterns of mutations. That will lead us to better prognostic indications and maybe to better drugs. In the future, maybe the drugs will work differentially. Right now, we don't have any that do, but I suspect there will be in the future. And that's when maybe some of these prognostic signatures become used in personalized medicine. We can relate these mutations to microsatellite instability, and we can relate them to stem cell biology. So I'll end there, and thank you very much for your attention. And I want to also thank, when I get a chance later on, our sponsors. But thank you very much.
So, any questions? So, okay. Pardon me.
Do you think the stem cells actually through the matrix, it's like the EMT structure, and that potentially what happens is the microenvironment changes, and somehow that gets
I do think that cells, we now know that cells live in a context of their matrix and their scaffold, as we heard. We learned at the AACR very clearly, they showed that these crypt cells in the colon, and who first noticed was Lieberkühn. Lieberkühn was looking at the microscope, and he noted these stem cells were next to things called Paneth cells. If you ever take histology, and these little chunky cells, and they're always flanked by them. Well, it turns out the stem cells can't survive without Paneth cells. So I do think there's something to multiple cells and other structures nearby.
And then the other thing is
That's absolutely true.
It wasn't discussed here, but hypoxia, where there's a lack of oxygen, turns on a whole set of different genes that become a very important thing. So tell me, Dr. Yateman, do you think that the microRNAs like you discussed will be used someday for therapy?
Well, I think the problem with microRNAs and all these things in therapy is how to deliver them. And my idea is to attach them to glass beads and inject them like we do TheraSphere, whether our interventional radiologists here. But I'm told that they tried to do this with siRNAs in the spheres, and they put them in gel, or they put them in liposomes, and they became very immunogenic. So that's failed. A lot of the drug companies have dropped out of the siRNA business because of that. But I don't know anybody who's tried to attach it to the microspheres, glass, because you can target liver and things like that. So hopefully someone will look into that.
All right, any other additional questions? Okay, well now, I do have one over here. Neal?
Just yawning.
Question. About 2% is actually fully translated as recognized protein. That's a hell of a lot of DNA that's back there that could be making a lot more microRNAs. How do we know the most development of these microRNAs that are necessary?
So, yeah, his question is that the 20,000 genes that Dr. Yateman described, it represents just a fraction of the total amount of DNA that's in each one of the cells. I think it was put at 2%. So the question comes about is, are there any other hidden mysteries in those other pieces of DNA? Are they there just because of various types of tandem duplications? And do they have a real purpose? And I think the only person that could really answer that is Dr. Yateman.
I'm not sure about that. Thanks, Jack. I think that we're sequencing everything now, right? So not one of those base pairs, 3 billion base pairs, is going unnoticed. So I think a lot of the things that were called junk DNA are probably regulatory elements, and they're regulating a lot of the gene expression. It's very complicated. I suspect we'll find more than just we found so far.
Okay, and we'll get back to Dr. Yateman after the next talk. And these things that we've heard about, whether it's stem cells or EMT, these are the new latest findings that we realize may be the reasons why chemotherapies have not been successful in treating tumors, or as successful as we would like. And we really need to understand how to kill cancer stem cells, and as cells go from epithelial to mesenchymal, to how to treat each one of them individually. So our last speaker, we've saved, of course, the best for last, is Dr. Paul Richter, and he is principal scientist at the structural chemistry labs of Merck. Paul has been involved in looking at the biotechnology of protein-protein interactions. For the last 35 years, he's developed high-throughput crystallography for being able to try to develop our understanding of protein-protein interactions. And, of course, this is where a lot of the advanced studies are going now to try to see if we can interrupt protein-protein binding as new vehicles of therapy. So we're looking forward to hearing about this from Paul, and hopefully he's going to give us a lot of crystallography structures with all the mathematics behind those so that we can have a better understanding. Paul?
Oh, I know you're disappointed. Okay. All right, first of all, I'd like to thank the organizers for giving me this opportunity to talk today. I don't get out of the lab much, so this is a real experience for me. One of the things, I guess, that not speaking that much outside of Merck, is the disclosure form that you have to fill out, where I have to disclose that I work for Merck. And I'm always interested in the kind of response I get when I say I work for Merck. I get, from some people, I get Merck, and then I get the sigh. And then all of a sudden, I know what it's like to feel like Darth Vader and work for the evil empire, so. What I wanted to talk to you today about was, given my perspective of being a principal investigator, what's it like? What kind of problems you run into? What kind of results do you get? Is it worth the time and effort to do the kind of work, or put in the time of effort to do the kind of experiments? Most of my experience has been doing experiments on the internet, on the space shuttle missions over 10 years with alpha interferon, and very recently have had the opportunity to plan for a mission on the International Space Station. So why don't I start? There's my disclosure. Oh, let me go back one. Okay. All right. So I was trying to think of how am I going to very simply explain what my experience has been. I'd say it's best captured by the Rolling Stones song, you don't always get what you want, but you get what you need. And that's been my experience. And that's also the experience of working with interferon as well. Alpha interferon was one of the first human recombinant proteins that people looked at in the 1980s. It made the cover of magazine. You've seen that somebody showed a slide today of something that was on Time magazine. Alpha interferon was on the cover of Time magazine. And it was supposed to be the cure for both the common cold and for cancer. It was so valuable at the time, the early days when we were working with it, when we'd purify a couple of nanograms of it, we'd have armed guards that would accompany the scientists going between buildings to do analysis. So that's how much hype there was for alpha interferon in the early days. From those early times, the hype died down, and they found that the only indication that it was effective in was hairy cell leukemia. So this was very good news for people that had hairy cell leukemia, and it was 80% effective. The bad news is that the entire population of patients who had hairy cell leukemia were already cured in the clinical trials. So when it was approved in 1986, the drug that was supposed to cure everything, really that wasn't making any money or doing anything at all. And then a few years later, somebody found that it had very good immunomodulatory effects, and it was approved as it met an unmet need for hepatitis C. And at the time, it's to this day, it's still the preferred agent for hepatitis C. And it cures about 40 to 50% of patients who have hepatitis C. And I'll just give you some background on protein. Let me see, before, I'm sorry. Okay, let me go over some pharmaceutical applications for crystalline biologics. When I say crystalline biologics, I mean most proteins that are of interest to the pharmaceutical industry. By far, the biggest use for protein crystals is in drug discovery. And most people are surprised, and this is using a technique called X-ray crystallography, where you actually can generate the three-dimensional structure from that. And people are always surprised when I say drug companies are really not interested in the protein. They're interested in the small molecules that bind to the proteins. And by far the biggest use for these structures is seeing small fragments or starting core compounds that they can make druggable. And sometimes they're very interested in how the small molecule binds and causes dysfunction in the protein, but they are also interested in the part of that small molecule that's open, that they can make that small molecule have the properties that you want, make it specific, give it the pharmacokinetic properties and the safety properties that you'd want to have in that final drug compound. Next would be, indication would be for manufacturing, where you can, just like they do with small molecules, is purify it, use a crystallization as a final step in a purification process. This is done routinely with most small molecule drugs. It's unusual for proteins. However, we developed a large-scale crystallization process for our interferon product, and every week in a plant in Brener, Ireland, on a kilogram scale, they purify alpha interferon by a simple process where they crystallize it and centrifuge the final product away from the impurities that are there. And it's a highly, how should I say it? It's a very desirable step by the FDA. You have your own internal quality control within your purification process. The third area where there's opportunity for protein or crystalline proteins is in product development. For 60 years, people have been injecting crystalline insulin suspensions, and in the case of insulin, it gives them a preferred controlled release effect and allows less dosing with insulin that would be in solution. And one area that I'm particularly interested in, and this is a problem with most protein therapeutics, is that there's no oral delivery, no oral absorption. So pulmonary delivery is of particular interest to me. I just want to point out also the size of the crystals. Now that's about, for structure determination, you're looking for a crystal, preferably something like 50 to 100 microns in size. You really don't care for the manufacturing process. For control release, you're looking for crystals in the range of about 5 to 80 microns in size to be able to fit through a normal tuberculin syringe. Pulmonary delivery, it's absolutely essential. I'm talking about systemic delivery from the pulmonary area of the lungs. It's very critical that you have 5-micron particles in order to get systemic delivery. All right. So about, it must be 15 years now ago, we were approached from the University of Alabama in Birmingham in collaboration with NASA, asking us would we be interested in doing protein crystallization with alpha interferon. And we said yes. And at that time, there was no hardware that was developed to do large-scale protein crystallization. And in collaboration with NASA and the UAB, we developed the protein crystallization. We developed the protein crystallization facility. And it looks like a relatively simple hardware. It consists of polysulfone bottles with an aluminum cap on it, which then fits into a rack. We're using temperature to induce crystallization. So we're trying to take advantage of two of the effects, major effects, that microgravity has to offer. One is the lack of or minimum sedimentation. The second is convection currents, because we're using temperature to induce crystallization. So with interferon, what we're doing is we keep our protein cold. We adjust the pH to 6. We're sitting right on the isoelectric point of the protein itself. And as we warm it up, we do a temperature ramp. And as we warm it up to 22 degrees, you hit 11 degrees and you get nucleation. So without any convection currents, you get, using a piezoelectric device, you get temperature gradient going across the tube. And you get a very, very nice, nucleation throughout the tube. All right? Go back. Okay. All right, so this is the first time that we had done this experiment in this kind of hardware, this kind of arrangement. We didn't know what we were going to get. So our first goal was, for this first experiment, was just proof of concept. And STS-51 was a 2-week mission. We did always our experiments. We have a flight hardware, and we initiate a ground experiment at the same time. After 2 weeks, we got our experiment back, and we found that, happily, we retained full biological activity. This is a photomicrograph of crystals from flight versus ground. You no problem seeing the differences in what the size of the crystals were. So it's 2.4-fold increase in the crystal dimensions. In the case of the flight experiment, 95% of the protein crystallized. And one of the interesting things is, as expected, you could take the 2 bottles, one from flight and one from ground, and you turn them over. The one from flight looked like a snow dome. You turn it over, and very nice, uniform, beautiful individual particles in there. Whereas in the ground experiment, the crystals were all stuck to the sides. So you could tell right away which were the flight, which were the ground experiments. The sample, we were happy to say that the flight hardware, that this processing and storage in the bottles did not affect protein integrity, crystallization, or biological activity. And the reason why we're happy about that was because normally this crystallization process that we do it in a day. We had to plan on having to set up the experiment 3 or 4 days before we had to activate it. It was 2 weeks where the experiment was ongoing, and then we weren't able to harvest the crystals until after that point. Okay. Now, after that experiment, we were all psyched. The crystals were still not big enough for doing structure determination. And we were feeling really good about these crystals. And then we tried to do the same experiment in a follow-up flight on STS-70. And lo and behold, we got what we didn't expect. We had a couple of scrubs before we could actually fly our experiment. We had to change out the protein. Things had not gone quite the way that we had wanted. And instead of getting a couple of very nice large crystals, what did we get? We got a shower of small crystals. And you could clearly see, if you looked at using particle size analysis, this is the ground experiment flight. You see, if you did a plot of the size of the crystals versus the probability of the distribution, it looked like in the ground there were several nucleation events that were taking place, whereas on the flight experiment, you got a nice bell-shaped curve around 5 microns in size. So a very, very beautiful distribution of 5-micron particles. Just turns out that 5-micron particles is like ideal for doing, for injection, for doing studies. And this was, at the time, this was the best crystalline suspension, uniform crystalline suspension that we had. And this was so good, particles were so good for this, that over the next 2 years, we had enough crystals to do animal studies to develop a formulation for making crystalline alpha interferon. And just to show you, this is one of the studies that we did. This is using 6 cynomolgus monkeys And typically, this is the profile of what interferon looks like in solution. Very rapid rise and clearance in a matter of 3 hours. With the crystalline suspension, you get a very low release over 48 hours. And that's what we're looking for. And we, at the time, the initial goal for coming up with a crystalline injectable formulation was 2 days. We were very happy to see this. But then they changed the ball game on us and said they wanted 1 week. So we were in competition with the pegylation, which is another method. This is a long chain polyethylene glycol that they attach or conjugate to the interferon. And they were able to get 1 week control release with that. Schering-Plough eventually went with pegylated interferon as their second generation. We found that with this crystalline suspension, if we put it into an oil-based formulation, we could duplicate those results. But ultimately, the company went with the other formulation. So this clearly worked out to our advantage. All right. Okay. This leads us to our next experiment. We decided, rather than look for structure determination, see what the differences were for purification manufacturing. So in STS 101, we were looking at taking crystals, take the crystalline suspensions that we got from both flight and ground, and comparing them using a battery of biophysical techniques. And one of the differences that we found is if you did protein analysis of the redissolved crystals, this is redissolving it in PBS, we found that in the flight crystals that over a range of different pHs and salt conditions that we got uniformly more protein to dissolve versus the ground crystals. And if you did use dynamic light scattering on the dissolved protein, you found that you had a lower polydispersity index, meaning that not only were you getting more of the protein dissolving, but that it was more monodisperse, more bioavailable than the protein you could generate in the ground-based experiments. That brings us to my last experiment that I did. This was on STS 107, and this was the fateful mission of Columbia in 2003. And we flew 100 1 ml bottles on this flight, and through a miraculous effort by the NASA recovery team, they were able to recover 3 intact bottles from there. It was clear to us, looking at the solution, that these bottles had taken enormous stress. And the purpose of this flight was for purification, so we were looking for very small crystals. And at first, I had looked at these solutions several times, and I couldn't see that sitting right in the middle of the solution was one very big crystal that was there. It was totally the opposite of what we had wanted, expected, but there it was. And when we did X-ray diffraction on that, it didn't diffract better than what we had seen before, but it was just a miracle that it had survived. The interesting thing from this experiment is that in the ground-based experiment, we're able to get a full angstrom's better diffraction than what we could previously get. So the message I get from this experiment was that, and I tell people this, that I learned how better to grow crystals on Earth by doing the rigorous experimental design that I had to do for doing microgravity. And so in summary, for drug discovery, in SDS 51, it was clear that we got larger crystals. For drug delivery control release, the two experiments, STS 70 and 101, we got more uniform suspensions. And these suspensions were used for animal studies, and they showed better dissolution properties. And for SDS 107, we did gain significant structural information from those experiments. What does microgravity have to order for bioprocessing opportunities? Applications where there's a critical need to minimize sedimentation effects and taking advantage of density gradients, convection currents. There are specific bioprocessing opportunities for biologics, for structure determination, for formulation and product development. Also, this is another area that there's not been much work done. That's in the development of small molecule drugs, structure-based drug design, and for small molecule crystal polymorph discovery. These efforts were a combination of a large number of people from Schering-Plough and from the University of Alabama, as well as NASA for funding. That brings us to CASIS. And I was really in the background when I had heard through the back door that I think Dr. Yateman had contacted Merck Oncology and had asked if any Merck was interested in doing protein crystallization. And at the time, Merck had not done any protein crystallization. And I think indirectly, in a roundabout way, they had contacted me and said, would you be interested in doing this? And of course, I jumped at the opportunity. It was 10 years where I hadn't been able to do any of these experiments. When they approached me with it, I don't know how to say it. It was like a gift from God. That's all I could say. We had come to the point in my previous work where we thought, it was just one experiment away from having, to prove that, microgravity had its value. The second thing that I was fortunate in is from the time that I had done the interferon work, we're also working heavily into biologics now. And biologics are monoclonal antibodies, vaccines, and biosimilars. The U.S. demand for biologics is supposed to exceed $100 billion by 2015. That's a startling number. And by 2016, 7 of the top selling drugs will be biologics. I mean, that's a shock even to a lot of people at Merck that things are moving so fast from small molecules to protein therapeutics. And with this big change, there's a need for advances in manufacture, storage, and formulations. This is reinforced in my head every day. The lab that I'm in, I look out my lab window, and there's a new $300 million biologics development facility that's going up next to me. So, I mean, I see the future. It's right in front of me. All right, so what happened was that after we were contacted, we were told, we'll make a proposal of what you would want to do. And it just so happened that in the year before we were asked, I was working on crystallizing a monoclonal antibody that's currently in phase 3 clinical trials for an immunological disorder. There are very few whole human antibody structures done. Most of the time, people want to get a structure of an antibody. They generate a fab fragment of that, and it crystallizes readily. Believe it or not, there's only been 6 whole human antibodies that were done. And we had crystals, and they diffracted to about 4 angstroms resolution. And we thought this would be an excellent opportunity to see if microgravity could give us the increased order in these crystals to be suitable for structure determination. And the second thing that we're interested in is a real problem with all monoclonal antibodies. And that is that the dose that they use, they're generally about 100 milligrams or so more in a dose. There's a brick wall of the solubility of these antibodies in the formulations, and it's about 100 milligrams per ml. After that point, the protein starts coming out of solution. So if you have to give a dose of 200 milligrams per ml, rather than being able to give a single injection, you have to be given a slow infusion in a hospital setting. So there is a real need for a formulation to allow you in a doctor's setting to be able to do a single injection. And we thought, we have crystals, why not see if we can develop a formulation where you can inject, do one single sub-Q injection under the skin and develop a concentrated dose of your monoclonal antibody. This is a picture, a photomicrograph of what these crystals look like. They're really spectacular. They're about 10 microns in size, and I can grow them readily any day of the week in 1 or 2 days. The real problem is doing it in microgravity, where I have to prepare my experiment 5 to 6 days before they go on to, into the Dragon module. And then the experiment is going to be activated another 4 days after launch. And then it's going to sit a minimum of 18 days before it comes back from orbit. And it's going to be another 3 or 4 days before I have to look at it. So just think of that, you got one shot. So something that very, very easily you can do in a couple of days, you have to plan on an experiment that has to give you the same results in a month's period of time. And that's a real challenge. One of the issues that I'm running into right now is mold. Under these conditions, I'm having real trouble preventing, microbial growth under these conditions. And I'm debating about whether I should add a preservative at this time to prevent it. I've been told by experts that as long as you sterile filter your solutions prior to going in, that I should be able to get around this mold problem, but we'll see. So there's a lot of things that you run into doing microgravity experiments that you have to think about where it's very straightforward on Earth. Something doesn't work once on Earth, you immediately make a change in one of your variables and you're good to go. But here you have to anticipate the possibility that you'll have scrubs, that you'll have delays, and you have to build in a lot of slop into your process in order to get meaningful results from that. This is the hardware that we're flying for the structure determination. It's a very simple device. This is called a 6-pack, and it's the high-density protein crystallization facility. And you put I don't know if anybody's done protein crystallization, but the classical method that you use is called vapor diffusion and hang drop method. And basically, you take a drop of protein and you put it over a solution that has, say, a higher salt concentration. And what will happen is that over time, the water, you'll get a differential in the vapor pressure between the drop and the solution below. And that you'll get the drop will dehydrate over time. And if you're lucky, you'll get supersaturation, you get nucleation, and then growth of single crystals versus an amorphous solid or a precipitate. that you would get. Your drop of protein goes in a cup that sits up here. These experiments are on a rod. So this six-pack, there's 5 of these in the hardware, and then all the astronaut has to do is just do a 180-degree turn of the crank here, and that brings this cup in close proximity to the reservoir solution that's soaked up into a sponge called Chromex that sits below it there. So that's the simple arrangement for these. We're doing our experiment at room temperature. So we have some thermal blocks or bricks that are maintaining the temperature in our experiment, and it sits in a little Velcro storage bag. So it's going to go up on the Dragon, attached to the wall, and the astronaut's going to take it off, put it into an International Space Station, activate it. It'll sit there for 18 days, deactivate it, put it back onto Dragon, and we're fortunate in this. We're going to get our experiment back in 18 days, hopefully. We do plan on, as a follow-up experiment to the structural studies, is going back in our PCF hardware and looking at all the other applications for crystalline suspensions. That is the drug delivery, purification, and storage of the bulk active. And this is all using monoclonal antibodies. And our hope is that we will find improvements in the quality of the protein that we wouldn't get on Earth. And already have some data to support that. In one of the early interferon experiments, when we looked at flight and ground, we found that there was a difference in the isoforms that were in flight and ground. So there is indication that you will get improved purification in flight. This is, I just explained to you what we're going to do on the SpaceX 3 mission in October. And this work is supported by a large number of people from both Merck in our structural chemistry group, as well as a protein characterization group, and it's done in collaboration with CASIS and with NASA. So that's all I have.
Well, this is very interesting. Do you think that as you look at other proteins that they may have different patterns, or they may make crystals at a lower rate or lower density than what you've seen for interferon? I mean,
I'm looking at Craig, and I know what he's thinking is that I guess it's good job security because every protein behaves different from every other, I guess that's one thing that really frustrated in the early days when we were doing protein crystallization with NASA. It drove the NASA engineers crazy. What do you mean that you get different? You'll set up 6 experiments exactly the same, and all 6 will behave differently. So.
Well, it could be with interferon you happen to pick the best one you could have looked at, or it could be it's actually the worst, and so the rest of them may yield crystals where we can't do it here on Earth. It'll be exciting to see that.
Go ahead. Paul, do you know where your experiment will be parked on the station? I'm thinking of your enemy. One of your enemies is like the treadmill.
I don't know. I don't know where it is. But obviously, we'll try to keep it away from the treadmill.
Tim?
Yeah. Yes. That's my hope, yeah. Yep. We've not looked into that, no. I am actually surprised that other pharmaceutical companies have not, and small biotechs have not looked into, using this kind of technology in general, outside of microgravity. Just the idea of treating protein crystals the same way that they do small molecules, Using I'm talking about using a crystalline formulation or a crystalline purification step. I think that Schering took a big chance in trying to identify, a crystallization step within their process. As far as I know, we're the only ones who do that.
Any other questions? Okay. Well, thank you very much. Oh,
I think there's one
I'm
question.
sorry. Was there another question?
Yes, right here.
Oh.
That's proprietary. We like to keep that proprietary.
Right. Okay. Question was, is there any indication, or could he tell us which particular types of maladies he may be looking at in terms of these antibodies he's discussing? And he could tell us, but then he'd have to kill us. So
that's right.
Good. All right. Now,
So thank you very much.
now Dr. Yaden for a wrap up and a benediction. Right.
Well, first of all, thank you to Dr. Pledger for moderating today. He did a wonderful job keeping us all happy. I want to thank everybody for attending this conference. We sort of went out on a limb planning this, I think, just 3 months in advance, and we had a great planning team and really pull it off. This is really operations at its best. Wanted to thank our sponsors, CASIS, VCOM, Spartanburg Foundation, Regional Foundation as well, and our exhibitors, Merck and MaxSource Avia, for really making today's event a success. We will do this again next year, so you can mark your calendar. We'll have a lot more planning this time to do it. So we think that it's an exciting venue. I can imagine that we'll see some results from Paul's experiments and others that are going up to station, maybe a venue to really promulgate the results of things that are done on station and things that are done in the Gibbs research labs, as well as VCOM's labs. So there is an optional tour of the Gibbs Research Institute that begins at 4 o'clock for those who are interested, and the directions are located in the front of the program. We opened the lab. We did a ribbon cutting last night, so you can actually go see what a stem cell lab looks like and a major laboratory looks like. Just housekeeping, don't forget to stop by the registration table to sign out for your CME credits, and please leave your evaluation forms and badges on the table in order to get your credits. Again, thank you for attending, and appreciate you coming today.